All right, in chapter number 3, we are going to start our journey down of discovering what kind of security mechanisms I would implement in my network architecture to secure the protocols and the foundation of our network. And this chapter is dedicated to securing layer 2. So we're going to be talking about things like port security. We're going to be talking about protecting the switch architecture from things like MAC flooding attacks and ARP poisoning. So we'll talk about dynamic ARP inspection. We'll talk about the concept of VLANs and how we can segment data in our network based on VLAN configuration. Why does that help? How does that protect us? Essentially anything that has to do with protecting layer 2. That's what this chapter is all about. All right? It's a big one, actually. This is a long chapter. It's going to be a lot of fun. With regard to the OSI model, layer 2 is considered to be the data link layer. This is primarily where switches operate, although other devices certainly have data link layer functions. My computer has a data link layer function. It certainly understands what MAC addresses are, and it builds a MAC address table or an ARP cache, if you will. But this is what Cisco refers to as NFP. NFP stands for the Network Foundation Protection. And the concept here is it doesn't matter how secure your applications are at layer 7. Doesn't matter how secure the transport layer is. If the foundation of the network's not secure, then the rest of the network isn't secure. It's kind of like building a house of steel on a bed of straw, right? The foundation sucks, doesn't matter how strong the house is. All right, so we're going to spend a lot of time focusing on how to protect that foundation before we get into some of the more advanced application layer stuff and so on. So let's talk a little bit about switching. This is obviously something that we reviewed when we did CCNA. So we're not going to get into a whole lot of detail here, but switches operate at layer 2 of the OSI model. And there's only two decisions that a switch will make with regard to data. What are those two decisions? Am I going to X the data or am I going to Y the data? Fill in the blank. It's a Mad Libs option for you guys. Am I going to X the data or am I going to Y the data?
Flood or forward.
Flood or forward. I would have also taken forward or flood. Right? Am I going to flood the data or am I going to forward the data? That's the only two decisions a switch needs to make. Is the data going to be sent out of an individual port, or is the data going to be sent out of every port except the port it came in on? All right, how do we make that decision? We make that decision based on a database that is maintained within the switch called the MAC address table, which is stored in content addressable memory. And that MAC address table gets constructed dynamically as data passes through the switch. So when a switch receives a frame, let's go, here is the processing of the data. On the left, we see the MAC address table for the switch on the left. On the right, we see the MAC address table for the switch on the right. Now, out of the box, these tables are empty. Agreed? These tables are empty. And the switch is not proactive in any means. The switch doesn't try to go out and discover who is attached where. It just sits and waits there for frames to come in. So let's say that PC over here on the left wants to send data to PC1, excuse me, wants to send data over to PC4. So PC1 sends a frame destined for PC4. Now the very first thing that the switch on the left is going to do is it's going to look at the source MAC address of that frame. Do you guys from our CCNA talk, do you remember what the format of that, first of all, what type of Ethernet is this most likely? And what is the format of that frame header? The type of Ethernet is Ethernet 2, developed by Xerox and other folks, Intel and Digital Corporation back in the day. Ethernet 2, and the format of that frame is very simple. 3 components to the frame header: destination MAC, source MAC, type field. Right? That's what's contained within the frame header. Destination MAC, source MAC, and type field. Type field is used to identify the transport protocol or the upper layer protocol that's encapsulated inside the frame, but the destination MAC and the source MAC, those are going to be used to identify where the frame is coming from and where the frame is coming to. So as this PC generates traffic, it's going to have a destination MAC, it's going to have a source MAC, and it's going to have that type field. Well, that source MAC allows me to map that host to that interface. So based on the source MAC address, the switch says, oh, you have a source MAC of A in this case. I'm going to go ahead and map A to port 1. It's a little bit more involved than that because there is one other component to the MAC address table that's not listed here, and that is the VLAN. We can also identify what VLAN this frame came in on. And when we talk about VLANs a little bit later on in this chapter, you'll see why that's important as well. All right? So now I've learned that piece of information. I've mapped MAC address A to port 1. Because the destination MAC, which is MAC address D, does not exist in the database. You can see right there, MAC D does not exist in the list. That frame is going to get flooded out of every port except for the port it came in on. We never send the frame back out the same port it comes in on, ever. All right? Well, guess what's going to happen? Switch on the right is going to receive that flooded frame on port 2. It's also going to map the MAC address of A to that corresponding port. And incidentally, it will also flood that frame out of every port except for the port it came in on. Well, except for in this case, D was already in the database. Because D was already in the database, we're just going to forward the frame out of port 1. There's no reason to flood it out of every interface. So PC4 is then going to respond, and the same thing will happen in the reverse. The wonderful thing about this process is that the more data that passes back and forth, the more data that moves back and forth between all these clients, the more intelligent the switches become because their database becomes more populated with relevant information. The downside to this process is there is no secondary check by the switch to determine whether or not this information is valid. It's very, very simple. If I see a MAC address come in on a port, I'm going to map that MAC address to that port, period. There's no way, there's nothing that the switch does by default that says, well, let me make sure that that client is on that port. Make sure it's not a spoofed MAC address or somebody's not trying to poison my table. The switch doesn't care. If it sees MAC address X on port 5, it maps MAC address X to port 5. Even if MAC address X existed somewhere else previously, it'll just move it to that port. This is the kind of the automatic nature of networking that makes us vulnerable. Now there's a couple of different types of attacks that would potentially occur here against this process. One, of course, is a poisoning attack, where I'm simply poisoning the entries in the database to trick the switch into forwarding frames out of ports it's not supposed to forward them out of. If I wanted to, for example, capture or insert myself into the middle of a conversation, I might spoof a MAC address just to trick the switch into thinking that that MAC address exists on my port when it doesn't. And that way that switch will start forwarding those frames to me. Another would be a MAC flooding attack. This data here is stored in something called content addressable memory. Let me write that again. Content addressable memory. And that's a finite amount of storage space for this information. There's only so much memory allocated to storing these MAC address entries. What happens if that memory gets full? What happens with any additional MAC address information? It doesn't get added, right? We don't drop the frames. We still process the frames, but we don't update the database, which means those frames subsequently get flooded. The switch becomes a hub for that particular type of traffic. So if I can fill up this CAM table with a bunch of bogus information, bunch of bogus MAC addresses, etc., by the time legitimate traffic has to come into the switch, there's no space to hold those legitimate MAC addresses, which means all the traffic for those clients is going to get flooded instead of forwarded. And if I'm a member or if I'm attached to that switch, I can now start capturing that data, start capturing that information. So that's called a MAC flooding attack or a CAM overflow attack. A couple of terms to describe that. All right. Now, one of the protection mechanisms that we have available to us in terms of switching is VLANs. At layer 2, I'll explain that in a minute. I was going to say something about layer 2 and its relationship to VLANs, but I'll talk about that in a second. A VLAN is a logical segmentation of a switch, essentially. And what it does is it creates these logical broadcast domains, if you will. So let's say, for example, I have a switch here, and I have 4 clients connected to that switch. 1, 2, 3, 4. All right? I have 4 clients connected to that switch. Now, by default, every interface on this switch is a member of a VLAN. VLAN 1. VLAN 1 happens to be the default VLAN on all switches, not just Cisco. VLAN 1 is kind of treated as what we call the native VLAN, if you will, the default native VLAN. It doesn't have to be the only native VLAN, but in the beginning, that's what it starts as. And this switch allows us to control memberships to those particular VLANs. So let's say that I've got IP addresses assigned to these individual clients. So this guy is .1, this guy is .2, this guy is .3, this guy is .4, and they're in the 10.10.0.0/24 subnet. So they're in what we call a broadcast domain. That broadcast domain allows us to control where that layer 3 traffic can go. If everybody's plugged into the switch natively, they're all going to be part of the same broadcast domain. They'll be able to communicate to each other. Now let's say that I've gone ahead and I've decided to segment that switch by assigning these 2 clients to VLAN 10, and I've decided to assign these 2 clients to VLAN 20. And we'll see what the syntax of that looks like here in a little bit, but essentially what I've done at this point is I've taken that switch and I've logically divided it into 2 different switches. One of the golden rules about VLAN communication, particularly inter-VLAN communication, is that I am not allowed to pass traffic from one VLAN to another unless it goes through what? Layer 3, a router. All right? So even though these guys still have their same IP addresses, even though they're technically configured within the same broadcast domain, this PC over here generating traffic in VLAN 10 would never be able to communicate to those PCs over there in VLAN 20. So 3 and 4 could talk to each other, and 1 and 2 could talk to each other on the same physical switch, and it doesn't matter that they're configured in the same logical subnet. There's a way that the switch handles this. If I was to put this into Packet Tracer, for example, and set up that configuration, so we've got a little bit of a network that we're going to construct here just to kind of demonstrate some of these concepts that I want to talk about. We're just going to have a little switch here with some 4 PCs here. We'll say that these PCs are going to be in the 10.10.0.0 subnet. Let me zoom in here. And this PC is going to be, like I said, .1, .2, .3, and .4. All right. So we'll set these up and we'll do some basic communication, look at how the cam table is built on the switch. And I'll show you guys some other things that I think are really important to understand. And these are the details that you may or may not be familiar with, even though you may have seen some of these discussions before. So let's go ahead and set up some of the IP addresses on our PCs. Again, these are just routers where I'm just using an interface to simulate. So IP address 10.10.0.1, 255.255.255.0. Oops, I forgot to turn on the interface. No shot. We'll do the same thing on here. Interface GI00, IP address 10.10.0.2. No shot. And interface GI00, IP address 10.10.0.3. No shot. And interface GI00, IP address 10.10.0.4. 255.255.255.0, no shot. That would be the wrong word there. All right. No shot. No shot. Of course, that is now recorded for posterity's sake. All right. All right. So if I go into my switch, all right, and I just do a show MAC address table. Sometimes there's a dash, sometimes there's not. I can see that I've already started to learn MAC addresses for these devices. And this is pretty typical for a router. Routers, when their interfaces come up, they start sending keep alives and stuff like that. Normally, I wouldn't see this MAC address information until the device itself generated some traffic. So I could have done a ping, for example, and let me do that actually. Let me go into interface VLAN 1, which is the SVI for VLAN 1, and we'll give that an address of 10.10.0.254, and turn that guy on. And I should be able to do a ping to 10.10.0, try that again, ping 10.10.0.255, and I should get a respond from some of these other devices in the topology. Because I'm pinging the subnet broadcast address, all these clients should get those pings and they should reply. So I got a reply from 10.10.0.1, I should get a reply from 10.10.0.2, 10.10.0.3, and so on. All right. Don't know why it's taking so long to do it, but we'll be patient here. There should be one more that we get a reply from. Now, if I look at the MAC address table, one of the things that you will notice about the MAC address table is that it is not only registering, that's good enough, not only is it registering the MAC address of the client, show MAC address table, it's identifying what port that MAC address is tied to, but more importantly, what VLAN that port is tied to. All right, and by definition, if a frame comes into one port that's in VLAN X, that frame is now only allowed to go to other ports in that same VLAN, period. There's absolutely no exception to that rule. If a frame comes in a port that belongs to VLAN X, it's only allowed to be sent out of all other ports that belong to VLAN X. Okay? Now, if I do a show VLAN, I can see what ports are assigned to what VLAN by default. And in this particular case, all of my ports are assigned to VLAN 1 by default. VLAN 1 exists by default. You can't get rid of it. You can't delete it. You can't rename it. You can't shut it down. It is the one VLAN that always has to exist. We also have some other VLANs here that are natively inherent to the switch, which are legacy VLANs for things like Token Ring and FDDI. Now, if I want to create a VLAN, it's really straightforward. I go into global configuration mode, I type VLAN 10, which allowed me to create VLAN 10. I can even give that VLAN a name, so I can say data 10, for example. And then I can create VLAN 20 and give that a name, data 20. And if I do a show VLAN, I can see that those two VLANs have been created in the database. So far, so good, right? We've created the VLANs, but the VLANs are not presently being utilized. Now, we'll get into assigning the VLANs in a minute. I don't want to jump too far ahead because there's a few things that I want to take a look at before we get to that point. Even though VLANs 10 and 20 exist in the database, they're not active on any of the interfaces. So we have a full communication capability between these four clients because they happen to be within the same broadcast domain. And they're all part of VLAN 1. In the same broadcast domain, meaning they're on the same subnet. And they're all part of the same VLAN. So going back to the slide here, a VLAN is a logical partition of my layer 2 network. That was what I described there. You have a switch. I've created VLANs 10 and 20. If I assign clients to those VLANs, they are now logically separated as if they were physically attached to different switches, even though they're physically attached to the same switch. So that's why we call it a logical separation. All right, multiple partitions can be created, and they coexist based on the fact that you just have multiple VLANs. In our case, we created VLANs 10 and 20, which means we've now created, logically, 3 separate broadcast domains. One for VLAN 1, one for VLAN 10, and one for VLAN 20. Each VLAN or broadcast domain usually falls within its own IP domain. That's not the way we have it configured presently. If you look at our topology, all 4 of these PCs are part of the same broadcast domain. They're in the 10.10.0/24 subnet, which means they're all part of the same room logically. PC1 is .1, PC4 is .4. All right? VLANs are mutually isolated, and packets can only pass through between VLANs through a router. I'm going to demonstrate that concept in this exercise here. All right? The partitioning happens within a switch. VLANs are a function of layer 2, not layer 3. VLANs are a function of layer 2. All right, which means that's something that we do in the switch. Hosts that are grouped within a VLAN are unaware that the VLAN exists. In other words, the client doesn't really know that it's in a VLAN. It knows that it belongs to a particular subnet, but it doesn't know that it belongs to a particular VLAN. All right? So I'm going to add one more component to this topology. We're going to add another switch in this case. And we'll call this DSW1. We'll call this guy ASW1. ASW stands for access switch. DSW stands for distribution switch. And I'm going to add a link here. And this will be gig 3.3 going to gig 3.3. All right, we'll power that guy on. And I'll just put some port designations on here. Gig 3.3. And we'll just put that in the middle since, right? And this is gig 1, gig 2, gig 3, gig 4. I think that's how I had it set up. No, 0 through 3. So this is gig 00 on that side, and then this is gig 03 on this side. Now there's a reason why I did this, because I want to demonstrate a couple of different concepts. I want to show you guys what it looks like to pass traffic over a link from multiple VLANs. We're even going to be able to do some Wireshark captures and see what the frames look like as they move from one VLAN to another. And then eventually we're going to segment these hosts apart from each other, put PC1 and PC2 into VLAN 10, and put PC3 and PC4 into VLAN 20. Okay? Probably something that you guys are familiar with. I mean, you've probably done this before. I don't know what, Bob, your background is, but it seems like you've done some of this stuff before, right? So let's go ahead and come into here, and I'm just going to change the name of this guy to ASW1, which stands for access switch, and then this guy will be DSW1, meaning that it's going to be basically my router in this case. All right? Now, before I get into the actual configuration, what is the difference between an access port when it comes to VLANs and a trunk port? An access port is usually where my hosts are connected. Those are the interfaces where the clients belong to a specific VLAN. And we're going to set this up. We're going to configure this in this topology. A trunk port is any interface. It doesn't matter what it's connected to. Usually it's switch to switch, but it doesn't matter what it's connected to. A trunk port is any interface that needs to pass traffic for more than one VLAN. But there's an interesting thing about a trunk port. When you guys did your CCNA test, you had to set this stuff up, right? You had to configure VLANs and you had to set up trunks. So this discussion is kind of helpful in that regard. All right? So a trunk port is any interface that has to pass traffic from more than one VLAN. All right? So let's say, for example, in our topology, I now want to kind of set up this network to where I'm going to have a SVI on here, a VLAN 10 SVI, if you will, which is going to have an address of 10.10.10. Well, we'll do 254/24. And I'm also going to have another SVI. SVI is a layer 3 interface on a switch that provides the ability to do routing for VLAN 20, and that's going to be 10.10.20.254/24. And on this switch, I'm also going to do inter-VLAN routing. On this switch between VLAN 10 and 20. And this interface here is going to be set up as a .1Q trunk, so that the traffic from one VLAN, the traffic from VLAN 10 and the traffic from VLAN 20 can pass over that particular link. All right? This PC here is now going to be 10.10.10.1/24, and it's going to be in VLAN 10. And we can get rid of this guy, so I'll just move that over here. Now let's just delete that. This PC is going to be 10.10.10.2/24. It's also going to be in VLAN 10. This PC right here is going to be 10.10.20.3/24, and it's going to be in VLAN 20. And I think you guys get the idea. This PC is going to be 10.10.20.4/24, and it's going to be in VLAN 20. Now you might be thinking about this, well, what does this have to do with security? Why do I care about all this stuff? It has to do with security for a couple of reasons. Because when you're implementing VLANs, there is an easy way to do it, and there's a secure way of doing it. Most people do it the easy way. But I'm going to talk about some of the concerns that we have if we're just doing it the easy way, which you may or may not be aware of. Even if you've taken these classes before, it might be something that somebody hasn't told you. So we've already created the VLANs on ASW1 to include VLAN 10 and 20. And again, show VLAN will show us that. Right? We can see VLAN 10, we can see VLAN 20. All right? I'm going to come back to this slide in a minute. We'll go over here and talk about configuring the VLANs. So step number 1, create the VLANs. Now I need to do that on DSW1. I haven't done that on DSW1 yet. So config T, VLAN 10, name data 10, and VLAN 20, name data 20. All right? That is the first step. Whenever you're setting up VLANs on a switch, you need to create the VLANs in the database. Otherwise, the VLANs are not going to be usable. The second step would be to assign the VLANs to your host ports. Now, actually, technically speaking, the only thing that you need to do to assign a VLAN to a host port is this command right here. Switch port access VLAN X. And that's what will assign the VLAN to the host port. I don't need the first command, switch port mode access. Don't need it. But we'll talk about why we put it in. It's really, really important. Extremely important, as a matter of fact. As a best practice standard, you should always be putting in switch port mode access. So let's go ahead and set up our host ports for VLAN 10 and VLAN 20. So I'm going to come into my switch here, ASW1, config T, interface range, GI 0/0-1. So I'm configuring both interfaces at the same time, and I'm going to say switch port access VLAN 10, interface range GI 0, spell it right, 02-3. Oops, forgot my GI. And I'm going to put those into VLAN 20. So I went into both, I just did 2 ports at the same time. You can use the range command to do multiple ports at the same time. So I went into gig 00 and 01, and I put them in VLAN 10. And I went into gig 02 and 03, and I put them into VLAN 20. If I do a show VLAN, I can see now that those ports are assigned respectively to their different VLANs. So far, so good. I did not put the switch port mode access command. We'll talk about why in a minute. But now I need to change the addresses on my computers. So I'm going to go into interface gig 00, IP address 10.10.10.1. And I'm going to have to put in a default route here. We're using routers as PCs, so we have to kind of trick them into thinking they're PCs. I'm going to go to PC2, interface gig 00, IP address 10.10.10.2. Normally, I would just set a default gateway on a PC, but because these are routers, we're going to use a default route to act as our default gateway. And that's going to point to the DSW1 interfaces. IP address here of 10.10.20.3. IP route 0.0.0.0, 0.0.0.0, 10.10.20.254, and finally PC4, interface gig 00, 10.10.20.4. So I'm just doing what the diagram says, right? I'm just setting up the new addresses for these clients. IP route 0.0.0.0. 10.10.20.254. All right. So, what have I done so far? On ASW1 and on DSW1, I created VLANs 10 and 20. Check. On gig 00 and gig 01, I assigned those ports to VLANs 10 and 20. And on gig 02 and gig 03, I assigned those ports to VLAN, gig 00, gig 01 to VLAN 10, gig 02 and gig 03 to VLAN 20. And then the last thing I did was reassign all my IP addresses based on the PCs and how they're attached to the network. Now remember what I said on the slide, the previous slide, I said the PCs don't really know that they belong to a VLAN. There's nothing I configure on a PC to tell it you're in this VLAN. They know that they belong to a subnet, but they don't know that they belong to a particular VLAN. The switch is what manages that VLAN membership. When traffic comes in from PC1 and it hits ASW1, the switch maps the MAC address of that PC to that port, right? When PC1 sends traffic to the switch, PC1 is generating a normal frame to the switch. When the traffic comes into the switch port maps that MAC address to that port, and then because that port is assigned to that VLAN, it identifies that traffic as belonging to that particular VLAN. So if I come into PC1 and I ping PC2, ping 10.10.10.2, first ping might fail because of ARP, but then the other pings will go through. And if I go into the switch and I do a show MAC address table, I can see now that the PCs are now mapped to their respective VLANs. Port 0 and port 1 are mapped to VLAN 10, and port 3 and 2 are mapped to VLAN 20. Now we're going to talk about tagging in a minute. At this point, tagging has not occurred. Contrary to popular belief, tagging does not occur at the ingress of the switch port. Tagging only occurs over the trunk link. So we can separate the traffic across the trunk as it passes from one side of the trunk to the other. And I'll show you what a VLAN tag looks like in Wireshark. All right? But there's absolutely no way for PC1 to talk to PC2 or PC3. No way at this point. We don't have routing configured. And even if I go ahead and set up the SVIs on DSW1, let me go ahead and do that. Config T, interface VLAN 10. So I'm creating layer 3 interfaces on this switch that correspond to the subnets that the clients belong to. So IP address 10.10.10.254, 255.255.255.0, interface VLAN 20. Wait for it to come up. IP address 10.10.20.254, 255.255.255.0. So if I do a show IP interface brief, I can see that those VLAN interfaces are now created on this switch. Forgot to turn them on. Interface VLAN 10, no shut. Interface VLAN 20, no shut. Show IP interface brief. So we can see that those interfaces are active. Well, not quite. They'll come up in a minute. They actually may not come up, and here's the reason why. We don't have any devices on this switch that are active in those particular VLANs, but we can see that they're created. The interfaces are created. Let me explain where we're trying to get to here, because I want to make sure that you guys completely understand this concept. All right? What I'm looking for, the objective, what I'm trying to accomplish in this particular case is I want this PC to talk to this PC. That's pretty simple. All that traffic simply has to pass through the switch. Because we're in a common subnet, we're not in a different broadcast domain. I don't need a gateway or a router to talk from one PC to the other. But in addition, what I would like to see is I'd like to have the ability to have this PC talk to that PC. Here's how that traffic is going to flow. This PC has a gateway configured. That gateway is this VLAN interface. Follow me so far? I configured a default route. If that was an actual computer, I would configure my default gateway as that VLAN interface. That traffic will come up to the switch. The switch is going to say that traffic is coming in on VLAN 10. So it's only allowed to go over interfaces that are participating in VLAN 10, which will be this interface eventually. It's not right now, but it will be eventually. That traffic will hit DSW1's layer 3 interface. DSW1 is going to act as a router, so it's going to know that it needs to route that traffic from that subnet to that subnet. And then that traffic will come back across this link, tagged into VLAN 20, and then it will pass down this link to that PC. This is what we refer to as inter-VLAN routing. Being able to move traffic from one VLAN to another. In order to do that, this link between the switches has to be a trunk. The link between the switches has to be a trunk because it needs to pass traffic for VLAN 10 and 20. But if I go into ASW1 and I look at the current status of that port, show interface GI33 switch port. That's one of the ways that we can verify this. I can see that that port is not acting as a trunk. It is an access port. And it's presently only in VLAN 1, which makes sense because we didn't modify its configuration. By default, every interface is in VLAN 1. We didn't do anything to that port, so it's in VLAN 1. Does that make sense? So I need to make that interface a trunk. Now, before we get too far off course here, let's talk about one other thing, and then we'll get into configuring the trunk interface. This command right here. This is where the security piece comes into play. This is a security class, so we're concerned about security. You should have already learned how to configure VLANs and everything else in CCNA, but the security piece we didn't talk about yet. Switch port mode access. A lot of people think that they implement this command to make the port a host port. There's two types of interfaces. There's a host port, which is access, and there's a non-host port, which is a trunk. That's the only two types of interfaces you can have on a switch. It's either acting as a trunk or it's acting as a host port. All right? Now, I saw you shaking your head about this command makes the port an access port or a host port. Why were you doing that?
Well, no, I'm shaking my head because you said there's only two types of ports on there. Because you said access and trunk.
Right.
But there's a third one. If you throw no switch port on there, it becomes...
Well, that's a layer 3 interface.
Right, but there
and that would only work on a multi-layer switch.
Okay.
Right?
I was just throwing that out.
Well, and if you really want to be technical, there's a fourth one.
Right.
Because then you have auxiliary VLANs that you can configure on an interface as well. But still functionally, from a layer 2 perspective, an interface is either a host port or a trunk port. From a layer 2 perspective. What he's talking about is converting a port to layer 3 so that you can put an IP address on it. And there's a command that you can execute called no switch port that does that. Okay? We actually don't have any ports in our topology that need to be configured that way. I'll show you something about that a little bit later. I think you'll find very interesting. All right? So either a port is going to be access or it's going to be trunk from a layer 2 perspective. All right? Now that being said, are my ports don't have this configuration. We didn't apply this configuration on the interfaces. If I come back to ASW1 and I do a show interface switch port, gig 00 is access, gig 01 is access, gig 02 is access, gig 03 is access. In fact, if I do a show switch port include access, you can see that all the ports are access. But I did not put the command switch port mode access. All right? There is a protocol that runs on Cisco switches. It's a Cisco proprietary protocol. It's called DTP, the Dynamic Trunking Protocol. All right? We may have some slides on this a little bit later on, but I'm not sure that there are. It's a pretty dangerous protocol. In fact, if I do a show interface gig 00 switch port, you can see that the negotiation of trunking is turned on this interface. See where it says negotiation of trunking on? That means that the protocol DTP is running on this interface. What Cisco did when they started creating their switches is they said, you know what? Switch-to-switch connectivity is almost always a trunk. Unless it's layer 3, it's almost always a trunk. So what we'd like to do is we'd like to come up with a way for the switches to just negotiate that trunk automatically without having to worry about it. So they turn on this protocol called DTP. There's two modes of DTP. There's desirable and there's auto. If you plug in a desirable port to an auto port, the trunk forms automatically. Voila, you got yourself a trunk, and you didn't have to configure it. From a security standpoint, this is a huge vulnerability. Because if I'm a client and I want to attack hosts on all VLANs, the only way for me to do that is to be connected to a trunk. That's what's going to allow me to start generating frames and send frames to every port, every VLAN. Well, if DTP is the default on the switch ports, all I have to do is generate DTP messages, and the port I'm plugged into will become a trunk. And now I can start doing a VLAN hopping attack, and I can start tagging frames and sending them to wherever I want to go. The reason why the switch port mode access command is so important is it disables DTP. That's the purpose of the command. The port will still become an access port if it doesn't get DTP messages. But if you don't put that command on the interface, it is highly susceptible to a VLAN hopping attack or a VLAN tagging attack, because all I have to do, and by the way, your CCNA does this, your CCNA will allow you to generate DTP frames. So all I have to do is start generating DTP frames on the interface, and that port becomes a trunk. And by default, all VLANs are allowed across that trunk. So now I can start tagging my frames, and I can start doing denial of service attacks or scanning attacks or whatever on every VLAN, even though I'm not technically a member of any of the VLANs. Does that make sense? So if I come in here and I go config T, interface range, GI00-4, how come that didn't work? Interface range. I guess I needed an N there. 00-4. I guess there aren't four. Okay. And all I have to do is say switch port mode access. Now if I do a show interface GI00 switch port, you can see not only is the port administratively set to static access. Before it was dynamic. In fact, if I go up here, you can see the port is dynamic auto. So that's the mode of DTP that port is running. But you can also see negotiation of trunking is now turned off. So now I'm protecting myself against a VLAN hopping attack. I'm protecting myself against a VLAN tag, somebody plugging into this interface and making it a trunk.
Does that apply to both VLANs, 10 and 20?
It applies to the port. The port is still a member of a VLAN, right? We can see here the port is in VLAN 10, right? And it was in VLAN 10 before. But if somebody plugged into this port and they wanted to do something bad, all they would have had to do is generate DTP messages. The port would have become a trunk automatically. When a port is a trunk, it's not a member of any VLAN anymore. It's a member of all VLANs, essentially. And now I can start tagging frames and sending them over that link to any VLAN I want to. So as a best practice standard, when you're implementing your host ports, make sure you include that command. It's just, and most people do, just out of habit, but they don't necessarily understand the purpose of the command. They say, oh yeah, well that command makes sense because this is a host port. And that command makes the port a host port. No, it doesn't. The port would become a host port anyway. That command turns off DTP. All right? This command explicitly assigns the interface to a particular VLAN. And a host port can only be a member of one VLAN, right? We can't have multiple data VLANs on a host port. All right? So when they say disables dynamic trunking protocol, that's what we're referring to with that particular command. Now what about our trunk port? Show VLAN, we looked at this. Show VLAN allows us to identify what VLANs exist. As we can see, all the interfaces are in VLAN 1 by default. VLAN 1 is an interesting concept. The general recommendation is to never use it because it always exists. You can't really get rid of it. You can prune VLAN 1 off the trunk, and we'll talk about what pruning is in a minute. And it will prune VLAN 1 for the data traffic, but it will never prune VLAN 1 completely because there's protocols that run on the switch that require VLAN 1. All right? So we've got our ports connected, gig 00, gig 01, gig 02, and gig 03. They're in their respective VLANs. Now our next step is to set up our trunk. There are two types of trunking protocols that exist. ISL, which stands for Inter-Switch Link. That is a Cisco proprietary trunking method. Cisco invented trunking. They actually kind of invented the concept of VLANs as well. Cisco didn't start in the switching space, but they acquired switching technology and then they kind of made it better. Pretty much what they do with everything, right? Sometimes, not always. Inter-Switch Link was kind of the very first way of defining that traffic belonged to a specific VLAN. Remember, we're sending traffic across this link. That link is not a host port. It is a trunk port. And in order to ensure that we can identify what VLAN the traffic is part of or is a member of, as it goes over that link, we have to tag it. We have to give it a little ticket that says you're in VLAN 10, you're in VLAN 20. And so what we're doing is we're creating essentially these tunnels, if you will, across this link. They're not really tunnels, but lanes, if you will, traffic lanes, that says all the VLAN 10 traffic goes over this lane, all the VLAN 20 traffic goes over this lane. We're not allowing that traffic to commingle. We can't communicate from one VLAN to another, but we are able to pass traffic for multiple VLANs. In order to keep that traffic separate, we have to tag that traffic as it goes over that link so that we know on the egress what VLAN it belongs to, and then on the corresponding ingress port what VLAN it belongs to. So there's ISL, which is extremely inefficient. An Ethernet header is about 18 bytes. And ISL, when you add ISL on top of that, it adds about 22 bytes of overhead. I think it's 22 or 24 bytes of overhead. More than doubling the size of the frame. So IEEE came up with their own tagging method called 802.1q, or what we commonly refer to simply as .1q. All right, 802.1q is another tagging method. All right. Interesting thing about .1q is it's only adding 4 bytes of overhead. Much, much smaller footprint than ISL. So we're taking our original frame, which is what we see right here. We're splitting between the source MAC address and the type field. This is probably going to be Ethernet type. In most cases, it's Ethernet type for Ethernet 2. And we're inserting this 4-byte shim. It's a 4-byte tag. Half of that, 2 bytes, is just saying this is a tagged frame. It's another ether type field. So this Ethernet type field is going to allow us to identify what's in the payload. This Ethernet type field is going to allow us to identify that it's actually a tagged frame. So we're saying, okay, this is a tagged frame. So process the data, process this information as the tag. Don't assume that that information is the data field. All right, so what's included in the tag? There's a 3-bit priority field, which is used for class of service. It allows us to mark our frames with priority. Just like we talked about yesterday with the DSCP field, the day before yesterday, the DSCP field in the packet header. The class of service field is our priority field for layer 2. So if we want to prioritize our frames, we can do that. They have to be tagged in order to do that, though. You can't prioritize frames unless they're tagged. Then we have this 1-bit field called the excuse me, the conical format identifier field. Yeesh. Conical format identifier field. It's essentially a token ring flag, which we don't care about, right? And then finally, and this is really important, the VLAN ID. It's a 12-bit field, which means we have 4,096 possible values. 2 to the power 12 is 4,096. This is literally where the VLAN number would go. So for VLAN 10, it would be 0, 0, 0, 0, 0, 0, 0, one more, 0, 1, 0, 1, 0, right? So that would be 10, meaning that the 8 and the 2 is turned on, 8 and 2 adds up to 10, and so on. You get the idea. For the 20 VLAN, it would be a 1, 0, 1, 0, 0, which would be 16 plus 4, which is equal to our 20. So we simply put in the bits in that field that match whatever the VLAN number is. That's how we can identify how a frame belongs to a particular VLAN, is because of this tag. And then the rest of it is just our regular Ethernet frame, our payload, and our frame check sequence. All right? Like I said, there's a common misconception that the tagging occurs on the ingress port. It doesn't. We only tag traffic over the trunk. We can associate traffic to a VLAN because the switch keeps that in the CAM table, it keeps that in the MAC address table, and we can associate the traffic belongs to a particular VLAN because of that, but as it goes over the trunk link, that's where the tag gets applied. So in order for us to actually set up the trunk, we have to tell the switch what tagging method we're going to use, if the switch supports both. Some of them only do .1Q. And we have to set the port as a trunk. So interface gig 033, switch port trunk encapsulation. And you can see this switch supports 3 options: .1Q for 802.1Q tagging, ISL for inter-switch link tagging, or negotiate, where the switches can figure out what they're going to do, which they'll revert to ISL if both of them are kind of passively negotiating. But we're going to go ahead and say .1Q. That means that whenever traffic passes over this link, make sure you're tagging it with that tagging method, .1Q. And then I'm going to say switch port mode trunk. That turns the interface into a trunk. I'll do the same thing on DSW1. Let me make sure I have my VLANs first. I think I created them. Yep. All right. Interface, oops, config T. Interface GI33, switch port trunk encapsulation .1Q, switch port mode trunk. I kept telling you guys, use your tab completion, right? It makes your life a heck of a lot easier. You actually don't even have to type anything in. I use the tab completion so you can see the whole syntax, right? But you could abbreviate all these commands and just type, you know, whatever you can do with tab, you can just leave, like SW would have worked, right? But I want you guys to see the whole syntax. Notice as soon as I made that interface a trunk, both of my VLANs came up. Because now I have an interface that's participating in those VLANs. Before I didn't. All the ports were in VLAN 1. If I do a show interface, try that again. Show interface trunk, I can see that gig 33 is acting as a trunk. Trunking mode is on, so it means it wasn't negotiated. We're using .1Q encapsulation. We'll talk about the native VLAN in a minute, but the native VLAN presently is VLAN 1. And also notice the VLANs that are allowed across the trunk. By default, all of them. By default, all VLANs are allowed across the trunk. Now I said there's 4,096 VLANs, right? 2 to the power 12 is 4,096. So what happened to 4,095? 4,095 is a system VLAN. It's reserved for system use. What happened to VLAN 0? Same thing. VLAN 0 is a system VLAN. It's used for system use. So mathematically speaking, we do have 4,096 VLANs, but only 1 through 4,094 are usable. All right? Now here's a little sidebar, because I guarantee you this is something that you guys probably don't know. If I do a show run here, you're going to see a command in here that almost always shows up. In fact, it pretty much always shows up in most switches. And it's right here. VLAN internal allocation policy ascending. Free lunch tomorrow for anybody that can tell me what that means.
Well, that was a pitch. I think did very good for you.
Free Sheets hot dogs.
2 for $1.
2 for $1, and I'll give you 10 of them. No.
It's gonna allocate some policy to something that's ascending.
No, it's the way it shows up in the VLAN table. Ascending is, I want to say it's when you do the show VLAN, if you can do the ascending, it starts at the lowest number and goes down to the highest, but I'm probably wrong.
That would be incorrect. But don't feel bad, because even in my CCNA class, people don't know what this means. And honestly, I have to be honest, I only learned maybe a couple of years ago myself what this meant, because I ran into it in a production environment. You were talking about something which you did know about, which is I can go into an interface, I'll do 3/2 in this case, and I can type the command no switch port. And what that does is that converts that interface to layer 3. You can do this on a multi-layer switch. You can't do this on a regular layer 2 switch, but on a multi-layer switch, you can convert an interface into layer 3. Now, what's interesting is if I go in and I type in VLAN 1006 and give it a name of test, it's going to give me an error, and it says, you can't use that VLAN. Now, I could come in here and I could say VLAN 1007, no problem. Created VLAN 1007 without an issue. That is because if I do a show VLAN, I can never remember the stupid command, show VLAN internal usage, that's what it is. I can never remember that command. It took VLAN 1006 away from me when I made that interface a layer 3 interface. VLAN policy ascending means whenever you're allocating a VLAN for some other purpose, some system use, which is what it does. Basically, it created an SVI for that interface, a virtual interface, a virtual layer 3 interface, and it took that VLAN away from me. And it does this in the extended VLAN range. Ascending means start at 1006 and go up. Descending means start at 4094 and go down. Right? Only reason I ran into this one time is because the customer was using extended VLANs and it would not let me create a VLAN. I could create all the VLANs around it I wanted, but it would not let me create that particular VLAN, but they had some layer 3 interfaces and was not aware that the switch stole those VLANs from me and used them, assigned them for internal usage to kind of virtually terminate that traffic to an SVI. Very, very interesting concept. All right?
I wasn't even close.
Nope. Sorry you don't get the hot dogs, but is 1006 one of the reserved VLANs? Roger asked a question, is 1000, I didn't remember if it was. No, it's not. 1005 is the last reserved VLAN. 1006 is the extended range. There's a normal range of VLANs, and then there's an extended range of VLANs. The reserved VLANs stop at 1005. So anything from 1006 all the way up to 4094 is considered an extended range. Not all switches support the extended range, but that's where that policy is. So if I come in here and I go into interface gig 3/2 and I type switch port, which makes it back to a layer 2 port, if I do a show VLAN internal usage, that VLAN is no longer used, so I can actually now create VLAN 1006. It released that VLAN back to be used as a regular layer 2 VLAN because the switch didn't need it anymore for the layer 3 functionality of the port. And you can change that assignment policy. You can either make it ascending or descending. A lot of times we like to change it to descending because we'll end up using some of the lower VLANs in the extended range for layer 2 stuff. And we'll leave the higher VLANs for whatever the switch needs it for. Does that make sense? So you can go in here and say VLAN internal allocation policy descending. Oops, gotta spell it right. Now if I go into interface gig 3/2 and I do no switch port and I do a show VLAN internal usage, now you'll see it assigns 4094 instead of 1006. So now this is a little piece of information you can go to your CCNA folks and say, I bet I know something that you don't know.
I'm about to blow some minds.
Yeah.
We had something similar that happened to work with a Nexus.
Yeah.
It stole like a 39.
So just a little piece of information. It's not anything that's part of this course, but I thought it was kind of interesting, and we saw that. So we've now converted this interface to a trunk. We've got our SVIs configured. We've got our IP addresses and our gateways configured on our PC. Will we have reachability? Well, the first thing to do is to test reachability within the VLAN. Then you want to test reachability to your VLAN interface, which is your layer 3 interface. Then we can check reachability across the VLAN. So if I come into PC1 and I do a ping to 10.10.10.2, that works fine. If I do a ping to 10.10.10.254, that should work fine in this case. Yep. If I do a ping to 10.10.20.254, that works fine as well. If I do a ping to 10.10.20.4, it's not going to work. But it shouldn't have worked. It shouldn't have worked because I didn't turn on IP routing yet.
Well, you put a default route on something.
I put a default route, so IP routing must be enabled by default. Show run pipe include IP routing. Oops, not IP route, IP routing. Interesting. It probably should, in the real world, it probably wouldn't have worked. This is not real iOS, so it probably worked. Let me see if I do this. Come on. Switch is acting strange now. No IP domain lookup. Make sure you use that. Config T, no IP routing. It must be turned on this platform by default. That's what it would have normally looked like. Without a layer 2 switch that has the capabilities of doing layer 3 normally doesn't have layer 3 turned on by default. So I would have to execute the command IP routing to enable that layer 3 feature. All right. So it did work because we did have show IP route. We did have the networks attached and whatnot. So let's take a look at what the tagging looks like for the traffic that's passing over the link. This is another reason why I love this program, is because I can do integrated Wireshark captures and we can see the data moving back and forth. It is the same on NXOS, Roger, absolutely. I'm not sure about iOS XR. Certainly iOS XE, it will be the same. Not quite sure about iOS XR. We'll take a break soon here, but here's my capture. We can see some spanning tree stuff. That's going to be good to look at a little bit later on. But let me go ahead and do my pings. 10.10.20.4, repeat 100 times. All right, so it should work. There we go. And what I should see in the capture is all those ICMP messages. And because I'm capturing this traffic on the trunk link, they should be tagged. Right? Let me come up here and grab one of these. And sure enough, there's my frame header. destination MAC, source MAC, .1Q tag. And if I expand the .1Q tag, there's the 3-bit priority field. There's the token ring encapsulation flag, or the conical format identifier. I'm not sure what DEI stands for. And then here's the VLAN ID. And we can see 1010 means that it's tagged in VLAN 10. There's my original type field that would have come from the PC before the frame was tagged, which indicates that it's a v4 packet. And then this is the v4 header and the ICMP payload. So this is what the tag looks like. 3, 4, plus 12, 16 bits, 4 bytes. Okay? All right. So what is a VLAN hopping attack? A VLAN hopping attack is a concept in which a client can start to send in tagged frames because they've negotiated or they've connected themselves to a trunk, and they can start generating frames that go to PCs in different VLANs. We don't need a router in this case because I'm connected to a trunk. And as long as I'm sending in .1Q encapsulated frames, the trunk, and as long as those VLANs are active on that switch, the trunk will just interpret those frames as normal frames. All right? Switch spoofing is probably the most common form of an attack that allows VLAN hopping, and that has to do with the fact that the port has DTP enabled. All right, could be an access port with DTP enabled. That's why we run the switch port mode access command. That will mitigate that particular vulnerability. The other is a double tagging process. Double tagging is not as useful because it allows me to tag a frame, but double tag a frame so that I would have to know, we'll see a slide that depicts this later on, but I have to know what the native VLAN is so that one tag can get removed and the other tag can remain. But it's not really very useful and not very practical. So I would say that the double tagging option is not something we concern ourselves with. Now, if I look at gigs 3.3 on DSW1, show interface gig 3.3 switch port, we can see that the port is configured as a trunk. All right? It is running .1Q encapsulation. Administrative mode means what was it negotiated to? And because it was hard set, there is no negotiation. Let me rephrase that. Operational means what did it negotiate to. Administrative means whether or not it's allowing negotiation. And because both of these values here are hard set, that means negotiation is not allowed. But interestingly enough, look at that. On a port that is set up as a trunk, DTP is still running. DTP is still running. It's not as much of a security concern because it's already a trunk, but it's still a waste of resources. There's no reason to be running DTP on an interface that is already set to a trunk. So one of the things that we can do is go into the interface, and this is also a best practice configuration, switch port no negotiate. Switch port no negotiate disables DTP on a trunk port. Do show interface gig 3.3 switch port, and we can see now trunking and negotiation is turned off. So do show run. Eventually we'll get to the point where you see do show run interface GI33, all of the commands that we would put on our trunk port as a best practice standard, but those are 3 of them so far. You may or may not have to specify the encapsulation type. You only have to specify the encapsulation type if the switch supports multiple encapsulation types. This particular switch model does, so we have to specify the encapsulation type. A lot of switches only do .1Q, so if you try to type this command in and it doesn't work, that's okay. It just means that the switch doesn't need it because it only does one type of encapsulation. All right? So when we say switch port no negotiate, that is used to make the trunk more efficient, but it's not necessarily a security concern. All right. Double tagging. Well, there's a couple of, let me see if I can kind of describe this. So I have an attacker that's connected to a .1Q enabled port already. So it's already a trunk port, which is probably not going to happen anyway, but let's say DTP is enabled on that port. Double tagging, by the way, would be kind of a waste of time if you're already connected to a port that's allowing tags, because then you could just tag your traffic into whatever VLAN you wanted it to be wanted to be a part of. But there is something about trunk ports that is very interesting, and I'm going to demonstrate this here in a second. It's called the trunk native VLAN. Let me show you what I mean here. So let me say I go into interface gig 33 and I say switch port trunk native VLAN 10. And it's going to start yelling at me because it has to be the same on both sides. Notice the port just went down because we have a VLAN mismatch. Enable interface GI 33 switch port trunk native VLAN 10. Right? The port will come back up because now our native VLAN matches on both sides of the trunk. Anybody have any idea what that native VLAN is supposed to do on that particular trunk interface? Show interface trunk. There, it came back up. Oops. Show interface trunk. We can see that the native VLAN across the trunk is 10. What does that do for the traffic passing across that trunk link?
Depends on tag, right? From tag traffic.
It is so that that traffic for that VLAN is allowed to pass across that link untagged.
I think Cisco's the only one who does that.
Yes.
Use it for voice.
Yeah. You can use it for a lot of things. We tend to use it to black hole traffic.
Yeah, the WLCs would need it.
Yeah. And we can demonstrate this concept. If I come into my PC here and I start doing some pings, ping to 10.10.10.254, repeat 1,000 or 10,000, and I go to my Wireshark.
Why would you not tag the information instead of setting a port you can send the information untagged?
Well, there was a reason why this existed in the past, because we used to have these things in networks called hubs. And hubs used to allow us to extend the length of our segment, but they were physical layer devices. They didn't understand VLANs. And you might actually want to have devices connected to that hub to talk to other devices in the same VLAN. So we would make the VLAN native on that trunk so that the devices on that link could still talk to those devices in VLAN 10. So the tag is going to get stripped off on the egress side of the port. And then anybody that wants to talk to that client can talk to that client. And then on the other side, we're still going to recognize that traffic still belongs to VLAN 10 coming into the other port. So you'll notice here,
It'll have the tag.
right, for all the other VLANs going across that trunk, the tag would be applied. All right, so you'll notice here, this is my VLAN 10 traffic. This is my ping from 10.10.10.1 to 10.10.10.254. It is untagged. All right, we don't typically put production traffic into this VLAN anymore, into this native VLAN. What we like to do is we like to use a VLAN that's not used. So what that means then is that traffic that flows over that VLAN is going to kind of get stuck into that VLAN. But you can use the native VLAN for management traffic. You can use it for voice if you want to remove the tag. Not generally recommended because then you're removing your layer 2 class of service markings as well. But in any event, there's lots of ways to use that native VLAN. Yeah, go ahead.
Is that the same as having a native VLAN 1?
Well, native VLAN 1 is the default native VLAN. Once I made VLAN 10 the native VLAN across the trunk, VLAN 1 became a tagged VLAN and VLAN 10 became the untagged VLAN. By changing the native VLAN to 10, it made VLAN 1 a regular VLAN across the trunk. All right? Now you can force the native VLAN to be tagged. as well, which is kind of counterproductive, I think. It's a global configuration command where you can say, okay, for the native VLAN, whatever it is, I'm going to go ahead and tag that traffic. So if I come into my switch, I haven't tried this on these switches before, but see if it works. Global configuration command, right? VLAN.1Q native, VLAN.1Q native, .1Q tag native, right? No options there. Do the same thing on DSW. Exit. VLAN.1Q tag native. So now if I generate my traffic from PC1, what I should see in Wireshark is that traffic is now tagged. Right, that traffic is now tagged. It's kind of a best practice standard as well, because essentially what you're saying in that case is it doesn't matter what the native VLAN is, tag everything, including the native traffic. We like to tag our traffic because it just allows us to identify where it's allowed to travel. There's a lot of misconception about how the native VLAN should be used. A lot of different arguments about how the native VLAN should be used. Some people choose to use it as a production VLAN. Some people choose to use it as a black hole VLAN. Cisco generally recommends that you use it as a black hole VLAN. In other words, you make the native VLAN an unused VLAN and then put that on the trunk as your native VLAN. So then all your untagged traffic essentially gets associated, if you will, to that VLAN. So what happens if I come into my switch, and let me demonstrate this. See if I can demonstrate this. Let's say I create VLAN 99 and I say name trunk native. I'll do the same thing on DSW. VLAN 99, name trunk native. And I go into interface gig 33 and I say switch port trunk native VLAN 99. Same thing on this guy. It's going to start yelling at me again. Interface gig 33, switch port trunk native VLAN 99. Now what I would have to do is modify my configuration slightly here. I think I can just do it with SVIs. Let's try that. I don't want to have to add more devices. So if I do a show IP interface brief, I already have a PC, or I already have a layer 3 interface in VLAN 1, 10.10.0.254. So I'm going to create interface VLAN 1 on this side. This is totally an experiment. I have no idea what's going to happen here. I mean, I have a general idea of what's going to happen, but I want to see if it works. IP address 10.10.0.1, 255.255.255.0. So I'm putting this SVI into VLAN 1. Make sure it's up and operational. So VLAN 1 is never tagged unless you specifically identify that the VLAN should be tagged. But in this case, we've identified our native VLAN as 99. Question is, will I be able to ping to 10.10.0.1? Yes. The second question is that going to go across the trunk link as a tagged VLAN, or is it going to go across the trunk link as untagged? You would think it would be tagged, right? Because the other traffic is untagged. VLAN 99 is the only untagged traffic. Yeah, and sure enough, we see that VLAN 1 is now tagged. So that's why they say go ahead and create a VLAN on the trunk that doesn't really exist anywhere and make it a VLAN that nobody's using, so that makes sure that all the other traffic in your network now gets tagged across the trunk, including VLAN 1. Does that make sense? All right. Actually, you know what? Well, even our native traffic would be tagged in this case because we did the VLAN.1Q native or tag native. Roger says here, native VLANs are a fun place to leave a honeypot. Yep. Any kind of stuff that you don't want to protect. But there's always arguments against it too. I've had people in class that say, well, this is why we use the native VLAN the way we do, and I can't argue with them. I mean, I can't tell them that they're doing it incorrectly because, I mean, really, in actuality, the native VLAN can also be a tagged VLAN, as we saw. We can tag VLAN 99 traffic. And it would be tagged in this case. If I created an SVI on ASW1 and DSW1 and VLAN 99, that traffic would be tagged as well because I'm telling the switch, tag everything. All right? What's the takeaway from this? And then we'll take a break. Make sure you're turning off DTP. There is one other thing that you can do, and that is called manual pruning. If I do a show interface trunk, we can see that all the VLANs are allowed across the trunk port by default. That doesn't mean all VLANs are active on the trunk. It just means they're allowed if the VLANs exist. These are the only VLANs that are allowed to go across the trunk right now. Okay? Now that being said, what if I did not want a VLAN to be allowed across the trunk? I can come into my interface and I can say switch port trunk allowed VLANs, and let's say I just want to allow 10 and 20. I'll do the same thing on DSW1. Usually you try to do the same thing on both sides. Switch port trunk allowed VLANs, 10, 20. Do show interface trunk. We can see now that the only VLANs that are allowed across the trunk are 10 and 20. So am I going to be able to ping from 10.10.01 to 10.10.0254, or 10.10.0254 to 10.10.01? The answer is no, because I've pruned VLAN 1 off the trunk. All right? That doesn't mean VLAN 1 is not functioning. If I look at my Wireshark, I should still be seeing things like CDP, spanning tree, and stuff like that. And if I look at the tag, well, this one's actually tagged in 10 because it's spanning tree for VLAN 10. But I should see some CDP datagrams here. And those are in VLAN 1. That's not going to get filtered. Those are protocols that are required for the functionality of the switches themselves. Only the data traffic in VLAN 1 is being filtered. So eventually I should see some more CDP datagrams, right? There's DTP also. DTP is also, well, that's VLAN 99. DTP is always sent over the native VLAN. That's an interesting concept. There's a CDP datagram, right? It's a wonderful thing about Wireshark. You can just kind of see what's happening. See what's happening on the network. All right? All right. Our next topic is a really basic topic, concept of CDP, the Cisco Discovery Protocol. Remember, this is our Layer 2 security chapter, and CDP is a Layer 2 protocol, Cisco Discovery Protocol. It's a proprietary protocol that allows us to identify directly connected Cisco devices. And in some cases, it works on non-Cisco devices as well. The reason why this is even a discussion in the security section is because it does allow us to glean or gather information about the network. And it's on by default on Cisco devices. Now, it's not just for discovering directly attached devices. CDP can be used for other aspects of configuration and management. For example, CDP can be used to identify a VLAN that a phone might belong to. It can be used to negotiate or manage power requirements for devices that require PoE, and so on. But the reason why we mention it in the realm of security is that there's two reasons. CDP could be used to glean information about the network, and we'll look at CDP in our little topology here in a minute. But also CDP can be attacked as a denial of service attack. I can actually generate enough CDP messages to a switch to cause that switch to crash, because it's going to have to try and populate its database with all the CDP information. Yersinia, I keep mentioning that tool, has a built-in attack mode for CDP. And what it does is it floods out a bunch of random CDP frames so that the device that's receiving those frames stops functioning or stops responding. So unfortunately, we don't really have a way of limiting the amount of CDP information that a switch is allowed to process. We can do some sort of control plane policing, which CDP would be processed at the control plane, where we can filter or rate limit the amount of CDP traffic we would allow up to the CPU. But there's really no way of like rate limiting CDP like we can do with ARP and DHCP and so on. All right. The best practice is to disable CDP globally if you don't need the service. Very, very simple. We simply go into our device and we type no CDP run. So if I go into my switch here and I do a show CDP, I can see that I'm running CDP. Cisco discovery packets are being sent every 60 seconds. With a hold time of 180 seconds, which means I'm going to hold CDP information in my database for up to 180 seconds if I no longer receive CDP information from that particular device. And we're using CDP version 2. If I look at my Wireshark capture, we can see that Cisco Discovery Protocol is sent at layer 2. The destination MAC address is a well-known, not multicast, but a well-known MAC address for these frames. The reason why I know it's not multicast is because that would start with a different OUI. Multicast frames start with a well-known OUI. 01000 Charlie, 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 Charlie. You can see that's CDP, VTP, DTP, PAGP, the Port Aggregation Control Protocol, or port aggregation protocol, I should say, and unidirectional link detection. All use the same MAC address. So, but what's contained within this CDP frame is information about the device. So I can see here that we're running CDP version 2. The time to live is 180 seconds. The device ID is the host name of the device, which is ASW1. It's running this version of software, Virtual iOS L2, Advanced Enterprise K9. So I can see the software version. I can see what the platform is. It's a Cisco platform. If it is advertising an IP address, I can see the IP address. I can see the port. So I received this CDP advertisement from Gig33. What are the capabilities of the device? This is written in hexadecimal format, but it's converted in the database to a code, in this case a switch. What is the VTP information? So I get to see VTP information inside of CDP as well. What is the domain name? So if I'm capturing CDP, I could actually potentially join your VTP domain. We'll talk about VTP later on, but I can join your VTP domain just by capturing that VTP information in the CDP advertisement. A lot of people aren't aware that VTP information is actually propagated through CDP, and so on. All right? So there's a lot of information that I can learn from these Cisco Discovery Protocol messages. If I type show CDP neighbors, I can see what that database looks like. All right? The device ID is the host name of the peer. Because these are not PCs, these are routers, they're going to show up. DSW1. The local interface is the interface that I received the CDP advertisement on. So that's my interface that's connected to that peer. The whole time is how long this information is going to stay in the database. If I don't continue to receive those CDP heartbeats or those CDP keep alives, which are sent every 60 seconds. The capability is what is this device capable of doing. RB means a router or a bridge. RSI means a switch or a router. So DSW1 can act as a router or a switch, and it also supports IGMP. IGMP is the Internet Group Messaging Protocol that's used for multicast management, to join and leave multicast domains. And then finally, the port ID is the neighbor's interface that they use to reach me. So I could actually develop a network diagram, or I could communicate how these devices are attached simply by understanding what the CDP information states. Now, if I want to disable this, let's say that I did not want to run CDP on the ports that are connected to my PCs, interface range GI 0/0-3, no CDP enable. That will disable CDP on those interfaces. The way you can remember it is that you can enable and disable interfaces. You can enable and disable CDP on the interface by using the no CDP enable command or CDP enable. If I do a show CDP interface, we can see now that gig 00, gig 01, gig 02, and gig 03 are no longer listed as running CDP. All the other interfaces are still running CDP, just not those particular interfaces. If I wanted to disable CDP globally, no CDP run. And that would disable CDP. Do show CDP. CDP is not presently enabled. Okay? I don't know. I think, I know that most STIGs require CDP to be disabled, but
Just on the outside interface.
okay, good. But that's what I would say is, yeah, they changed it. That's what they used to say, yeah, you can't run it, but it's a really useful tool. And quite frankly, it's required in a lot of cases, especially if you're running voice, because the phones get their voice VLAN ID through CDP. So my recommendation would be just to disable it on interfaces that you don't have control over, or interfaces that go to domains that you don't have control over, like the internet, like an extranet, and so on. Now, there is another protocol. It's not mentioned in the book, but I'll go ahead and mention it here. It's called LLDP, the Link Layer Discovery Protocol. It's disabled by default on devices, but if I want to enable it, I just simply type LLDP run. It's very similar. I'm going to go ahead and enable it on both of these devices. LLDP run. It's very similar to CDP. In fact, it is essentially the same thing as CDP in essence, except for its open standard. So if I do a show LLDP neighbors, or show LLDP first, let's analyze it the same way we did before. LLDP advertisements, well, they're sent every 30 seconds, and they have a dead timer of 4 times, not 3 times, so 120 seconds. Show LLDP neighbors, I can see that I'm getting essentially the same information, the host name, the local interface, the hold time, the capability, and the remote interface. The nice thing about LLDP, though, that makes it a little bit more useful than CDP is that it's a lot more customizable. It actually uses something called TLVs. Let's see if we should be seeing some LLDP messages coming across here. Right there. It uses these things called TLVs, which stand for type length value fields, to carry information about the data. And I'm not seeing them defined as TLVs. Yeah, there we go. TLV type, TLV length, and then here's the TLV value down here. A TLV, we see this in a lot of different protocols. EIGRP also uses TLVs. TLVs provide us the ability to containerize information. And they're generic containers, like Tupperware containers. Type allows me to identify what is contained in the container. So think of that like writing a sticker on the box that says this is lettuce from 2 days ago, right? That's the type of data. The length is how big the container is. In this case, it's 4 bytes. And then the capabilities is the actual payload. It's what's inside the container. So TLVs are generic containers that allow us to encapsulate all kinds of information. And because we're using these generic containers to contain that information, we can essentially put anything we want inside those containers. I'm not sure what all the different TLVs are for LLDP, but we could probably customize just about any one we want. It looks like it's a 7-bit field to identify. It's kind of strange. It should be, that's an 8-bit field, just the last bit's not being used. Yeah, it's kind of weird how they have this broken down, being that it's 7 bits or 8 bits. the hex dump suggests that it's an 8-bit field. Let me click on that again. E0E04. But I'm not sure where they're getting that number from. It doesn't look like it's quite lined up with the binary string there, because 0E, I can see where they're getting the 0 from. I can see where they're getting the E from, because E would be 14, which would be a 111, because that'd be 8 plus 4 plus 2. But I'm not sure where they're getting the 04 from. I guess it's kind of carried over into this field here. Yeah, so it is. These two fields are being represented in this hex dump. So it looks like it is the first 7 bits is the type, and then the remaining. So it's overall it's a 16-bit field, but the first 7 bits are used to identify the type, and then the last remaining bits are used to identify the length. Kind of a weird thing. Usually we see them broken up into nibbles or octets or something like that. Anyway, it doesn't really matter. The point is that these type length value packets or frames pretty much provide the same functionality that CDP does. The other thing that's interesting about these TLVs is that you can, rather than going onto the interface and saying LLDP run or enable versus LLDP disable, is you can set it to receive or send. So I can say I want to transmit LLDP information, but I don't want to receive LLDP information. So I can say LLDP receive, do show LLDP interface. Doesn't like that command. Oh, because I put a do in front of it. Show LLDP interface. And I can see for gig 3.3, in this particular case, it's transmit and receive is, I forgot to do interface gig 3.3, no LLDP transmit. Do show run interface gig 3.3, show run interface gig 3.3. All right, so yeah, I'm receiving LLDP, but I'm not transmitting. Show LLDP interface gig 3.3. Yeah, and it says I'm no longer sending LLDP messages, but I'm receiving them. That's kind of unique to LLDP that you don't have in CDP. In CDP, you can either enable it or disable it on the interface, but with LLDP, you can enable it to transmit or enable it to receive or disable it in those cases as well. All right, our only really major security concern here is whether we have it on or off. Are we going to allow CDP in our network, or are we going to disallow CDP in the network? And then these are some of the defaults. All right, how often CDP advertisements are sent, whether or not they're enabled or disabled on a particular interface is critical as well. All right, so if I want to disable CDP, no CDP run globally, or no CDP enable on the interface. All right, so the last topic that we'll talk about today, which hopefully we'll be able to finish in the next half hour, it's normally something that we spend quite a bit of time talking about, is access control lists. All right, now ACLs are a very interesting concept. Fundamentally they're kind of basic, right? An access control list is a way for us to create a static packet filter or frame filter or segment filter that allows us to filter data passing through an interface. But oftentimes access lists are not only used for packet filters. They can be used as packet classifiers. So if we're setting up a QoS policy and we want to create a class map to put traffic into a particular class, we can use ACLs to send traffic to a particular class. If I want to set up a NAT policy, for example, and based on that NAT policy, I want to match traffic that's going to be natted, I can create an access list that actually matches traffic to be natted. All right? Now, there are many, many ways to create these access lists, and I do hope that after our discussion right now that you guys will actually feel like you've actually learned something about access lists, even though you've had some experience with them in the past, because there's a lot of different types of ACLs that we can create. We're typically used to just creating static packet filters, right? Standard or extended ACLs based on match conditions for IP address and port numbers and so on. But we can create filters for ether type. We can create filters based on MAC address. All kinds of access lists that we can create. In fact, if I come to my device here and I do a config T access-list, spell it right, you can see here that I have all kinds of options for creating an access list. I can do it based on IP. I can do it based on MAC address. I can do it based on the protocol type code. Protocol type code. So if I say 200 permit, what kind of types do I have? These are hexadecimal type codes. We're talking about ether type, ARP, IPv4, IPv6, etc. MPLS access lists. DECnet, that's old school, don't do that anymore. AppleTalk, don't do that anymore. So there's all kinds of different types of access lists, and even in other versions of iOS, we have even more capabilities besides what we have here. So an access list, most people will associate access lists to the process of filtering traffic, but access lists can also be used to classify traffic. Here's an example. I'm just going to make something up, but let's say that I wanted to create a route policy that says, let's go ahead and send all of my HTTP traffic to this IP address. That's going to bypass whatever my default routing policy is. I might come in here, and don't worry about the syntax right now, I'm just going to demonstrate. IP access dash list extended HTTP redirect. All right, this is beyond the scope of this class, but I just want to give you an idea. So I can say permit TCP any EQ80. So that's my HTTP traffic. And then I can create a route map called policy-based routing, and I can say match IP address HTTP redirect, and then I can come in here and set IP next hop 1.1.1.1. So what I did in this case is I created an access list that matched HTTP traffic, but I wasn't using the access list as a traffic filter. I was using the access list as a traffic classifier, saying, if this traffic is HTTP traffic, do this. So there's many, many ways that we can use access lists. They don't have to be just strictly packet filters. We're going to focus on the application as a packet filter, because this is a security class, and that's naturally one of the things that we do with a packet filter is to filter traffic based on an access list. There are two types of ACLs that we can create on a Cisco device: standard and extended. A standard ACL is going to be any access list that filters on source address, period. We can only filter on the source. It could be a MAC address, it could be an IP address, but it's only going to filter on the source of the traffic. 90% of the time, we're going to use standard ACLs for classifiers. Like, this traffic is going to go over the VPN, or this traffic is going to get NATed, or this traffic is going to be policy-based routed, or whatever. Extended ACLs can filter on a bunch of things. They can filter on protocol, they can filter on source IP, destination IP, source port, destination port, source MAC, destination MAC, all kinds of things. We have a lot of flexibility when it comes to creating an extended ACL. And it gives us the ability to really match specific conditions for that filtering process. So extended ACLs can be used as advanced classifiers. That's what I did with the HTTP traffic. I had to because I was matching on port, specifically destination port. But the other thing about a standard extended ACL is it gives me the ability to be very specific about what I'm matching. All right, and we're going to go through some examples, and I'll show you guys some examples as part of the process. All right, so standard or extended could apply to layer 2 addressing, layer 3 addressing, possibly layer 4. It's a little bit different with IPv6. There is no concept of standard ACLs with IPv6, only extended in IPv6, and only named. And that's another concept as well. This idea that we have named or numbered. Notice that numbered is identified as a legacy syntax and named is identified as a modern syntax. The reality is that numbered doesn't really exist anymore. Even numbered ACLs get converted to named. Let me show you what I mean. First of all, I just want to kind of describe the difference, right? Traditionally, what we would do is if I wanted to create an access list for whatever purpose, I would just simply go into global mode and I'd say access-list. I'd give it a number, permit or deny, and I would have some argument. Don't worry about the syntax. We'll learn the syntax for the arguments in a little bit. And then if I wanted to add to that access list, I could say permit TC, well, I can't do that. Let's just do permit 10.10.10.1, 0.0.0.255, and 10.10.10.10, and let's do, well, that really wouldn't do any good. Let me do this. There we go. Well, now it's not going to let me do it. But that actually defines the meaning of what I was saying. Traditionally, when I was creating numbered access lists, whenever I added an additional line, so this is a 3-line access list, actually 4 lines. It didn't add the 4 line. What it would do is it would simply add the next line at the end of the access list. But iOS is much smarter than that now. Because of the way access lists are processed, which we'll talk about in a little bit, the router is smart enough to say, you know what, you can't add that rule because that rule is already trumped by another rule that you already created. Now, if I do a show run, pipe section access-list, this access list will look like a normal numbered access list in the running config. And it only took 2 of my lines, but we'll talk about why that is in a little bit. But it looks like your kind of traditional legacy access list. However, if I do a show access-list, the router has converted this to a named access list, and they've just called the named access list 10. So they took the number that I used to create the access list and they made it a named access list. So I can actually come in here and say IP access-list standard 10, and I can now edit that access list as a named access list. So my point is that even though you can still use the legacy syntax to create an ACL, it's pretty much being converted to a named ACL by the router. All right. I know it's a lot of information. We kind of jumped ahead a little bit because the syntax is confusing. We haven't talked about the syntax yet. Don't worry, we're going to get there. All right. So the takeaway from this slide, and what's really important for this particular exam, you need to know the difference between standard and extended. All right. You need to know what a standard ACL filters on. You need to know what an extended ACL filters on. Standard ACLs filter on source only. Easy to remember because standard starts with an S, source starts with an S, right? Extended ACLs filter on everything. Extended starts with an E, everything starts with an E. All right? All right. And as far as creating ACLs, we pretty much use the named mode these days. Although on the test, almost all the ACLs on the test are numbered. So they still use the legacy syntax on the exam. Access list 149, access list 50, access list 20. We're going to learn the syntax. Okay? So this slide here kind of breaks it down. A standard ACL only filters on source. And there's 2 ways of doing it. You can use legacy where you use a number, or you can use the modern syntax where you use a name. Extended ACLs filter on everything: protocol, source, port, destination, port, options, the kitchen sink, everything. All right? And same thing, standard versus, or legacy versus modern syntax. What is the general purpose of an access list? There's two actions that an access list will take against traffic. I'm either going to permit the traffic or I'm going to deny the traffic. It could be I'm going to permit the traffic to be classified, or I'm going to permit the traffic to flow, depending on how I'm applying the access list. Going back to this example here, this was the access list that I created for my policy-based routing. Okay? And I said basically in line 10 there, 10 in this case represents a sequence number. I said basically in line 10, if you're web traffic, you're going to get policy-based routed. But I could come in here and do a IP access list extended HTTP redirect, and I could say 5 deny host 1. Let's do a different host, 5.5.5.5 any EQ80. Deny TCP. All right. Now if I do a show run, do show access list, I now have two lines in this access list. One is denying an individual host, the other is permitting the rest of the hosts. But the deny is not saying we're denying HTTP traffic, it's saying we're denying HTTP traffic from being policy-based routed. So we're not denying the traffic to flow, we're denying it to be policy-based routed because that access list is being applied to that route map, right? That route map is referencing that access list. So this is an example of a classification ACL. Now, we've already gone way beyond what you need to know for this test regarding access lists, outside of the actual basic rules that we haven't talked about yet. You're not going to have to know about policy-based routing for the CCNA security. That's stuff that we learn in CCNP security. But I'm trying to give you some additional information that I think would be helpful. So let's start to talk about some of the basic concepts of an access list. This is definitely something you would need to know. The 3 Ps rule. You can only have one access list applied per interface, per protocol, per direction. Now, what does that mean? If I have an IPv4 access list applied to this interface in the inbound direction, I cannot have a second IPv4 access list applied to the same interface in the same direction. I would have to combine those two ACLs together to create a single ACL. Could I have an IPv4 and an IPv6 access list inbound? Yes, because those are different protocols. Could I have a v4 access list applied inbound and outbound? Yes, because those are different directions. See what I'm saying? One ACL per protocol, per interface, per direction. Protocol, we're talking about protocol stack. We're talking about protocol stack, which means v4, v6. We're not talking about HTTP and FTP and Telnet. We're talking about protocol stacks. All right? So that's the golden rule number 1. One ACL per interface, per protocol, per direction. Assuming it's being applied as a filtering ACL. All right? The direction is always from the perspective of the router. Let me explain what I mean by that. If I create an access list, let me go into interface gig 3.2. I'm just going to do a no switch port so I have an interface that I can play with. If I want to apply an access list to an interface, I simply say IP access-group, and I reference the number that I created, and then I can specify whether that access list is going to apply to that interface inbound or outbound. So if I say in here, on that particular interface, I just applied access list 10 to that interface, which actually effectively does nothing, because the very first line of the rule says permit everything. But you understand what I'm saying. Any traffic that now tries to come into that interface is going to get processed against that access list. Whatever's denied is not going to be allowed to come into the interface. Whatever's allowed is going to be allowed to come into the interface. That is the whole point of applying an access list to an interface. But it has no bearing on what happens in the other direction, because the ACL is only applied inbound. It's not applied outbound. All right? So we always apply our access lists to the interface in the direction that we're trying to provide filtering. And we could have an ACL inbound and another ACL outbound, but our match conditions would have to match specific traffic flows that would match whatever we're trying to filter. All right? All right. So here's a couple of examples of some numbered ACLs. Access list 10. The 10 represents the number. Each one of these individual entries is called an ACE, access control entry. This happens to be a 3-line ACL. Now the very first thing, and this is also an extremely important concept that you need to understand about an access list that has multiple entries, is that the ACL is always processed from the top down. Always. I try to match the packet against the first rule. If the first rule matches the packet, I do whatever that rule says. What are the two actions that a rule can perform? What are the two actions that a rule can perform? I know you guys know this. Permit, deny. I'm going to permit the traffic or I'm going to deny the traffic. That's it. We're matching the packet, literally what's in the packet header, right? Source IP, destination IP, source port, destination port, whatever's in the header, we're matching it against the rule. If it's permitted, the packet passes. If it's denied, the packet is dropped. Those are the only two actions we can take in an access list, permit or deny. All right? Once that rule has been applied, we stop processing the rest of the access list for that packet. We don't go and search the whole access list and find out what quote unquote is the best rule. Whatever rule matches the packet is the rule that gets applied. Once that packet has the rule applied, we're done with that packet. We move on to the next packet. As I go down this list, I'm checking each rule against the packet. What happens if I get to the end and none of the rules match the packet?
Should be a default deny, but if there's not,
Well, there always is a default deny.
so it'll just get denied.
Yes. If a packet has not been permitted by an explicit rule, it will always get denied by the implicit rule at the end. At the end of every access list, it doesn't matter what kind it is, it could be standard, extended, named, numbered, there's always an implicit deny at the end of every access list. So unless the packet was explicitly permitted by a rule that you wrote, the packet will get denied, period. There's no exception to that rule. Now, you can effectively eliminate the use of that implicit deny at the end by doing a permit any, and a permit any simply allows everything. That's what we have in this access list here. This permit any makes this access list completely useless because the very first rule in the access list is permit everything. You all right there? Now the router in this case was smart enough. If I do a show run access dash list, the router was actually, or show access list, sorry. Control E. I'll get there eventually. The router was actually smart enough. Well, actually not in this case. Oh, it's because it's a standard. What I was going to say is the router was smart enough to reorder those rules. But it actually wasn't in this case.
Yeah, so you have to put what you're filtering after that any. The any's on the top, so it reads from the top down.
Because the any's at the top, any rule after that is going to be irrelevant.
Yeah, it always matches the first thing it matches.
Top down, the first thing it matches, it does that. Now, if I try to come in here and say access list 10, deny host 10.10.10.1, it's going to give me an error. And it's giving me the error because it says, you've already permitted everything else. And it's trying to add this rule at the end, but it can't add the rule because the rule would be useless. I've already permitted everything else, so I can't deny a specific host if I've already permitted everything else. Sorry?
Well, you
I can undo the permit, or I can come in here and I can edit it like a named access list. And I can add the rule based on these numbers here are sequence numbers. And I can add a rule to say in front. So rule 5 is going to be to deny that host. So I can insert lines. This is what you didn't used to be able to do traditionally. So now if I do a show run or show access list, I can see that it added that rule 5 before rule 10. That's why people tend to use named ACLs these days, is because you have that capability of inserting lines and even renumbering the ACL. The problem with traditional access lists is it didn't allow us to do that until now. Pretty much even traditional ACLs are converted to named ACLs. So, all right. So what are the takeaways here? The golden rule is that every access list is processed from the top down. By the way, that is in, there's a couple of pages ahead, the general rules for ACLs. So you may not have to write them down. They're already in the book. But every access list is processed from the top down. As soon as there's a match, we do whatever that match says, deny or permit, and we stop processing the packet based on that rule. There's an implicit deny everything at the end of every ACL. So if something is not explicitly permitted, it will be denied. Our more specific rules go towards the top. And actually, that's required now by design. The iOS says you can't put a rule. I don't want to deny network 10 and then try to permit host 10.10.10.10 afterwards. Because the host 10.10.10.10 is going to get denied by the deny network 10. So our more specific rules go towards the top. Because there's an implicit deny at the end of every access list, that means that every access list has to have at least one permit. Because if I've got a bunch of deny rules, deny, 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 and there's an implicit deny at the end, what's going to get permitted? Nothing. See what I'm saying? All right. Now the point of this particular slide is nothing like that. The only point of this slide is this is a standard ACL, and that's an extended ACL because of the numbers. That's all they're trying to demonstrate here, is that there are specific number ranges that are reserved for standard and extended. We're not talking about the wildcards. We're not talking about the syntax, but I thought I'd throw some of that in. All right. A named ACL is written with a name. Essentially, the syntax is identical. The only difference is you don't have to put a number in front of each rule. We actually go into ACL configuration mode by typing in a standard or extended ACL. IP access list standard, IP access list extended. Now if I do an IPv6 access dash list, you will notice that I don't have an option for standard or extended. Just give it a name. Because in IPv6 we can only do extended. There is no standard access list in IPv6. Also, there's no wildcard matching in IPv6. It's all regular subnet mask or prefix matching. All right. Let me see if there's one more thing. We've got about 8 minutes left here. And I do, yeah, we'll probably take a little bit more than 8 minutes because I do want to finish the next topic that's part of this discussion, and then we'll get into some of the other details tomorrow. One of the other things I wanted to mention, let's say show run, or show access list. Let's say that I've got this access list here, access list 10, and it's got these sequence numbers, 5, 10, 20. You can see that the sequencing is automatically in groups of 10. So every time I add a rule, it's going to add another sequence number by 10. So the next rule I add would be 30, next rule I add would be 40. But, you know, access lists kind of grow. We start adding lines in between. All of a sudden, we don't have enough lines to put rules in between. So if I said, for example, IP access dash list standard 10, and I put in 6 deny 10.10.10.10.5, and then 7 deny 8, you know, whatever. I'm just filling up the rules, right? And 8.
But you don't even have to do that. You can just name all 3 of those 8, and it'll just push it down. So if you go and if you just made all those 8, it would just push it down automatically.
It would not. Once the number is already taken, so if I did another, are you saying like do another 8?
Yeah, so just leave the 8 there and then put 11.
Duplicate number.
Is that just because it's standard? Because in extended,
Probably. Standard does tend to act a little bit differently than extended. But I've run into that situation before. That's why I knew that it wouldn't let me do that. We could try it with extended. But yeah, you would have to do like a no 8 and then put in another 8. But all right, so we could try that with extended and see what happens. I have seen that standard does tend to act a little bit differently than extended as far as the way it takes the syntax. We can try that real quick. IP access, and it could be a code thing too, right? Maybe Nexus does something different or another XE software does something different. IP access list extended. Let's give that, well, we can't do tab completion because we're not in the right mode. IP access list extended HTTP redirect. And let's do 5 deny TCP any EQ. I don't know, 69, whatever.
you know what? I'm wrong. Because
Yeah.
I'm thinking of ASA where you do line number. So
right.
You would go in, so
Yeah.
I'm on the wrong thing. So
Okay. Yeah. So it did say duplicate sequence number. So in other words, if my sequence numbers, that actually is kind of good because that tells me that I can't just simply just start plugging things in. Do show access list. Now I've run into a situation where my sequence numbers are all taken up. And what if I wanted to add something between, it's funny how it did 8 first and then 9 and then 7 and then 5 and then 6. It's actually doing well, it's kind of weird. I thought it was doing the length of the packet, but 1 is less than 5. So I'm not sure how it's deciding to do that. But in any event, everything up to 10 is taken, right? Unless I want to go before 5. So one of the things that you can do is you can do IP access dash list renumber. Let me make sure, let me think of the standard. I can never remember the stupid syntax for this. It might be just access list renumber. No, let's see if we have to go into the name. IP access dash list standard 10. Nope. I'll get there eventually. Resequence, that's what I was looking for. I can never remember the stupid syntax for that. So I can actually resequence an access list. So in other words, I can just change the numbers. So I'm going to reference the access list. In this case, it's 10. I specify the starting number, 1,000, and then I specify the increment. So I could say 1,000 if I wanted to. Now if I do a show access dash list, we can see that that access list has been renumbered. So now I have plenty of space to put other rules in between.
Can you increment this?
No, no decimals in binary at all. Everything is hard, no floating point numbers at all. So, you could increment by 1, but that would be kind of counterproductive.
I just was curious if inside access list,
Yeah. So it has to be whole numbers. I'm not sure what, you can always tell kind of what the limit is. So I can do it every 2 million, 2.14 million if I wanted to. Yeah, and I could start with any number. That number is not actually random. has to do with the size of the field in the payload. All data is contained within fields. They could be 16-bit fields, they could be 20-bit fields, they could be 10-bit fields, and that number is a power of 2. That just happens to be the size of a particular field, right? I would say that's 2 to the power of 32, but I think that's 2.4. 2 to the power of 32 is 2.4 million, I think, or 4.2 million. So that would have to probably be 2 to the power of, it's not 2 to the power of 16, because that'd be 65,000. I guess it doesn't really matter. Let's do 2 to the power of 20. Let's take a wild guess. It's close. Nah, not that close. Yeah. Anyway, you get the idea. So there's lots of things that you can do with these ACLs. I was gonna do the wildcard masking today, but I think we'll just start with that in the morning because that's our next discussion. Let's just kind of review this slide real quick. ACLs are processed from the top down. As soon as there's a packet match, we perform that action and we stop processing against the access list. Our more specific rules tend to go at the top, because it makes more sense. There's an implicit deny at the end of every access list. And finally, every ACL must have at least one permit statement. Okay? All right, so tomorrow we're going to start by talking about bitwise masking. A lot of people, when they talk about access lists, they talk about access list masking in the form of wildcard masking, which is a different concept. Bitwise masking, completely different concept. All right? So we'll see you guys in the morning. All right, so the next thing that we're going to talk about that we didn't get a chance to talk about yesterday in our journey about access lists is wildcard masks. More specifically, bitwise masking, which is what we use to match, to perform match conditions within access control lists. This is slightly different than what you would see for, like, for example, what you would use if you're doing inverse masking for network statements for routing protocols. In this particular case, everything that we do in access control lists is a bit-by-bit matching scenario. Now remember from our discussion earlier, when it comes to an access list, we're trying to permit or deny specific types of traffic through the access list, whether it's to classify that traffic, to perform a function against that traffic, or whether it's to permit or deny traffic to flow through an interface. So one of the things, there's really two challenging things. If you haven't dealt with access lists in the past, there's two challenging things that you have to deal with. Number one, what is the general syntax of an access list, and how do I organize my rules so that they're as efficient as possible, and that they're allowing me to process the data appropriately. And then the second is, how do I write my wildcards so they're also as efficient as possible, and they match the exact conditions that I'm looking to match. So let's go ahead and go through a few examples here. Talk a little bit about this wildcard masking option or bitwise masking option to give you an idea of how we would actually calculate these values. And hopefully you'll learn a little bit here about the difference between an inverse mask and a bitwise mask, okay? So let's start by just saying, what is an inverse mask? And it's not something that we typically will use with access lists, although it appears that they are inverse masks in most cases with access lists. But an inverse mask is exactly what it sounds like. It's the opposite of a regular subnet mask. All right, so an example would be if this is my regular subnet mask, 255.255.255.0, the inverse of that would be 0.0.0.0.255. All right, simple enough. If this was 255, 255, 255, 128. Then the inverse of that would be 0.0.0.127 and so on. All right? Because all I'm doing is I'm taking the 1 bits and I'm converting them to 0, and I'm taking the 0 bits and I'm converting them to 1s. And you might say, well, why would I do that? Why would I ever need to write a mask in the opposite way, right? We don't see this typically with IPv6. Whenever we're doing an access list in IPv6, or whenever we're doing any kind of routing configuration in IPv6, the use of an inverse mask is never used. So even in access lists for IPv6, we don't use wildcard masks, okay? But the question is, why would I ever do this? And the reason is, and the ASA is also unique, by the way. The Cisco ASA, which is Cisco's firewall platform, never uses wildcard masks either. It does everything in regular masks. But when it comes to ACLs, we use these inverse masks, if you will, to define our match conditions. And this is done on a bit by bit basis, which is why it's called bitwise masking, because we don't actually have to create an inverse mask that is consecutive zeros followed by consecutive ones. The ones and the zeros can be anywhere in the mask. All right, and we're going to see I'll demonstrate some of those concepts in a minute here, and we'll take a look in the command line, what that looks like in the command line as well. All right, so for example, when I am matching a rule, and let's say this rule right here, access-list 10 permit 10.10.10.0 0.0.0.255. So that's what a standard numbered ACL rule would look like. Okay? So when I'm matching a rule, the ones in the mask mean I do not care what the corresponding bits are in the address portion. The zeros in the mask mean I do care. So what does that mean actually? That means that if I'm comparing the IP address and the subnet mask, and remember, I'm trying to match this rule against a packet that's being processed by the device. And I'm saying, does the packet that's being processed match this rule, or does it not match the rule? All right? So what does that mean from the perspective of the access list that I created here? It means that the packet would match the above ACE if the packet starts with, let me try to spell that right, starts with 10.10.10. Okay? And that's because of the wildcard mask. We have 3 zeros here, which is 24 binary zeros. And we have 10, 10, 10 in the first 3 octets. So these 3 zeros here mean that when I'm matching the packet against the rule, I'm comparing the packet bit by bit, and I'm saying that every bit in the first 24 bits have to match. Because this 255 here represents 8 ones in binary, represents 8 ones in binary, the last octet does not have to match. All right, so the packet, all the packet has to start with is 10.10.10. And this is the most basic way of looking at a wildcard mask. All right, but you're going to see potentially all kinds of different wildcard masks. For example, you might see something like this. Access-list 10 permit 10.10.10.0 1.0.0.63. that is a perfectly valid wildcard mask. All right? Now again, if you go back to the general rule is ones in the mask mean I do not care what the corresponding bits are in the address, and the zeros in the mask mean I do care. It's a little bit more challenging to recognize what's matching and what's not matching in this particular case because the ones are kind of commingled with the zeros. All right? Now over time you'll get used to it and you'll understand that the first octet would be a 10 or 11 and then the last octet would be a 0 to 63. But if we evaluate it from a binary perspective, it will always get us the right answer. So my goal here is to say, okay, when I have a packet that gets received by the router or the switch or whatever, and it's being matched against this rule, will the packet match? So let's say that the packet we received a packet of 11.10.10.45. Is it a match? Let's find out. All right? So if I compare this in a bit by bit fashion, 10 is 0, 0, 0, 0, 1, 0, 1, 0. That is equal to 10 in the address. 1 is equal to 0, 0, 0, 0, 0, 0, 0, 1, which is equal to 1 in the mask. So essentially what I will do in this case is I'm going to say, you know what? The last bit, because it corresponds to a 1 in the mask, the last bit is just going to be an X because it can be anything. That's what the 1 in the subnet mask of the access list represents. It means that I don't care what the corresponding bit is in the address. It can be a 1 or it can be a 0. So anything that's going to match is going to have at least a 00000101 in the address portion of the first octet. So if I kind of break this down, that means that either 10 or 11 would be okay in the first octet. Make sense? Because I'm comparing this portion of the address with this portion of the mask. This portion of the address with this portion of the mask. Now, the next two octets are zeros, all zeros, which means that these have to be an exact match. And then the last octet, we have a 63 in the wildcard mask. So if I take the last octet, which is a 0, 1, 2, 3, 4, 5, 6, 7, 8, that equals a 0 for the address portion. And I take a 63, 1, 2, 1, 2, 3, 4, 5, 6, that equals a 63 in the mask. What does that tell me about what bits I care about and what bits I don't care about? It tells me that I don't care about these bits. Because again, the corresponding bits in the mask are a 1. Whenever I have corresponding bits in the mask that are a 1, it means I don't care what the corresponding bits are in the address. 1, 2, 3, 4, 5, 6. Okay? So, what does that match? That matches 0 through 63. Because this is the 64 column, this is the 128 column, doing our binary math. That's the 64 column, that's the 128 column. Those bits have to be a 0 because the corresponding bits in the wildcard are also 0. Does that kind of make sense? Okay. Now, it can get pretty crazy. It most likely won't, and it certainly won't on the exam. The wildcard masks that you're going to see on the exam are going to be very basic masks, but you can get pretty creative with these wildcard masks. When I took my CCNA lab the second time, they gave me a task of redistributing RIP routes into the EIGRP domain, but they said you could only redistribute these particular subnets, and you could only do it with a single access list, a single line access list. So I had to do bitwise matching to identify specifically what wildcard mask would match particular subnets to get into that domain. So how about something like this? Let me clear some space here. What if I had something like this? Access-list 10, permit, and I'm just going to make something up, 8.16.0.128, and I'm going to do a .3 or 3.7.25.31. Okay? Of course, you would never probably see this in the real world. It's not very practical, but it is completely legitimate. There's nothing wrong with this access list, right? If I come and I paste this into my command line, it's perfectly acceptable to have that rule. All right? If I do a show run, section access-list, all right, you can see that it accepted that access list, no problem. All right? That's because in access lists, all we're doing is bit-by-bit matching. That's all we care about. So it's really simple to kind of identify what would match and what wouldn't match as long as you follow that concept. 8 is a 0000100. All right? That is 8. And dot 3, or 3, is 0000111, which means that these 3 bits don't matter, XXX, which means that this would match 8 through 15. Simple, right? The last 3 bits can be any value. They could be zeros or they could be ones. If they were all zeros, the value of that octet would be 8. If they were all ones, the value of that octet would be 15. 16, 0001, 0000, that's equal to 16. And 7 is 0000111. That's equal to 7. Which means, again, the last 3 octets don't matter. So this would match 16, and then it would match 16 plus 7, right? So it would match 16, 17 through, what would be 16 plus 7? 23. All right, so basically we can just simply say 16 to 23, right? Because 16 plus 8 would be 24, but the 8-bit always has to be off because the corresponding bit in the mask is a 0. So that bit can never change in order for the packet to match the rule, is what I'm saying. All right? So what about the third octet? 1, 2, 3, 4, 5, 6, 7, 8. That equals 0 in the address portion. 25, 1, 2, 3, 4, 5, 6, 7, 8 is 25, right? 16 plus 8 plus 1 is 25. Agreed? So what would match in this particular case? Well, again, all I simply do is I say, okay, those 2 bits can be anything, and this last bit can be anything. So in this case, we would match 0 and 1, and we would also match 8 and 16, and we would match, well, I put them in order, I guess, 9, and we would match 16 and 17. And 24 and 25. Did I miss any? All I'm doing is I'm saying these bits can be any value. If these two bits were 0, if these two x's were 0 and this x was a 0, then it would be a 0. If these two bits were 0 and this x was a 1, then it would be a 1. If this bit was on, it would be an 8. If this bit and this bit was on, it would be a 9. If this bit is on, it would be a 16. If this bit and this bit is on, it would be a 17. If this bit and this bit it would be on, it would be a 24. And if all three of these x's were on, it would be a 25. See what I'm saying? So that's why we call it bitwise masking as opposed to wildcard masking, because wildcard masking ends up kind of giving you the impression that the masking is done in with consecutive zeros followed by consecutive ones. And that's what you're going to see on the exam, by the way. Any kind of reference to the exam is going to be a basic inverse mask. They don't really have any bitwise masking questions on the test. But it is something to consider because you can get pretty creative with these access lists. And if you can find a way to match all the criteria or as much of the criteria as possible with a single line, that's going to make your access list a lot more efficient. Plus, it also provides for job security because anybody else that looks at it has no idea what you did. All right? So they think that you're the only one that can do it. So that's essentially what the inverse mask is. It allows us to do match conditions. Now, what if I would have done something like this? And I'll make it a pretty basic one. Okay? What if I would have come in here and I said 10.10.10.0 0.0.3.255. Now this is an interesting concept because if I was to copy this and paste it into my configuration and then I do a show run section access dash list, you would see that the router would actually convert this access list to a different format. So I put in 10.10.10.0 and the router changed it to 10.10.8.0. So at least the router is smart enough to say, well, the access list rule that you put into place isn't valid syntax, so we're going to convert it. Well, let's find out why the conversion took place, right? Because certainly we know that 10.10 is going to match to the two zeros here, so we don't have to worry about that. But the third octet, 00011010, that equals 10, and 3 equals 000000111. That equals 3. So what the router is saying, wait a minute, you set a bit in the address that corresponds to a don't care bit in the wildcard mask. So rather than have that bit fixed or set, this bit becomes a don't care. And so I set the access list rule to that least common denominator that includes the 8-bit, but the number 2-bit gets turned off because it's a don't care bit. Make sense? So the router is smart enough to say, you've identified a bit in your address field that we don't care about. We're going to ignore that bit, and we're just going to go ahead and set the access list to the bits that are fixed. All right? So you might see that from time to time if you're doing a configuration, and you might be like, wait a minute, that's not what I typed in, but now when I go look at my access list, it's completely different. That would be why. The router is basically doing the math for you and saying, the don't care bits are literally don't care. We're going to set all those to 0, and we'll create our access list with only the bits that we care about. All right? So just to review on this particular slide here, the wildcard mask and subnet mask are differ in the way that they match binary ones and zeros. Wildcard masks use the following rule. If the wildcard mask bit is a 0, we match the corresponding bit value in the address, and I care what that bit is. So that bit is fixed, if you will. Basically, this is just a summary of what we just talked about. If the wildcard mask bit is a 1, it means that the corresponding bit in the address is a don't care, and that bit can be anything. All right? They're often referred to as inverse masks, and as you were mentioning, EIGRP is going to use this concept as well, so is OSPF. But in OSPF and EIGRP, they literally have to be inverse masks. You can't do bitwise matching in EIGRP or OSPF. So, but with access lists, we have that capability. We can do bit-by-bit matching. All right? So the next thing we're going to talk about is, well, you know, how do we apply these access list rules? How do we verify their operation? This is just an example of a standard ACL. In this particular case, it's a pretty basic concept. We've got global configuration mode here. We're going to create an access list using the legacy method. This is going to be a standard ACL because it's a number 1. Remember, standard ACLs range from 1 to 99. This is a deny statement. And in this particular case, we're denying an individual host. Now, with a standard ACL, you can specify an individual host by using the host keyword. You could use a quad 0 wildcard mask to do an exact match. Or in the case of a standard ACL, you don't have to do either. If you just specify an IP address, the router or the device will automatically assume that you're talking about a host. When you're dealing with extended ACLs, that's not an option. In an extended ACL, you actually literally have to specify whether or not it's going to be a host or whether or not there's a wildcard mask. But in this case, we're denying that particular host, and then we're permitting everything else. The keyword any means go ahead and permit everything else. All right? So that's great. We did create an access list globally in our configuration. But until that access list is applied to a process, or until that access list is applied to an interface, its function is nothing. Right? It's not going to be doing anything in our topology if we don't apply the access list. In this particular case, we're going to our gig 00 interface, and we're saying IP access group 1 in. So we're taking that access list, we're applying it to that interface in the inbound direction. Remember, it's always from the perspective of the router that you're applying the configuration to. And in this case, we're applying it to that router for company A. So what is the end result of applying this particular access list? Client 10.10 is only going to be able to communicate within the subnet, but client 10.10 cannot leave that network. Remember, this is a standard ACL. And in a standard ACL, we're filtering based on source address. Source address with a standard ACL. All right? How do I verify whether or not I have an access list applied? There's a couple of different ways we can do it. Show IP interface is very useful because it will actually literally tell me if I have an access list applied to that interface. Not show interface, but show IP interface. Conversely, we would see the same thing if it was show IPv6 interface, to see whether an IPv6 access list might be applied. Show access list will show me the configuration of my access list within my command line. And you can see that it did in fact convert this, at least in the show output, it converted it into a kind of a named format, not a numbered format, because it gave us the sequence numbers for each of the individual ACEs that we put into the access list. All right? And I think that's a little bit different than what we applied here. Yeah. So this was an access list where we denied an individual host. This is an access list where we're denying a portion of the subnet, right? Addresses 0 through 15, if you will. All right. Here's an access list applied, no access. We're denying that individual host, we're permitting everybody else. So this is what we would consider to be a legacy standard ACL, and this is a named standard ACL. But they both kind of get treated the same in modern iOS these days. We do have other options to provide security for our devices. We were talking about ACLs in a sense that it's just simply an access list that we create globally and we apply that to an interface. Those would be considered a PACL. A PACL is just a port-based ACL. A port-based ACL. But I can also apply what we call a VLAN ACL, or I can apply an ACL to the virtual interface of the device. Now, we'll probably not get into, well, I guess we could take a look at the VLAN ACL, an example of that. I don't think the book has an example. Yeah, they do have kind of an example. We'll take a look at a couple of those examples and apply them to our topology. So let's start by looking at a port-based ACL. And this is the interesting thing that you will see with switches that a lot of people are not aware of that you have the capability of doing. Even if the switch is a layer 2 device, it still has the capability of having access lists applied to the interface. Even if they are layer 3 referenceable access lists, meaning that we're matching conditions based on layer 3. So we'll kind of adopt this ACL here to what we're doing in our environment. So let's say, for example, in our topology here, going back to our topology, I don't want PC1 to be able to talk to PC number 2. Now, PC1 and PC2 are in the same subnet, right? So typically, we've always kind of associated applying access lists at our broadcast domain boundaries, meaning on our router interfaces. But I should have the capability of applying an access list directly on gig 00. In addition, I want to go ahead and provide a filter based on MAC address, not on IP address. So, and that's an interesting concept. I actually have the capability of applying an access list based on MAC address rather than IP address. So let me do a little bit of discovery here. I'm going to go to PC1 and I'm going to do a show ARP. So 10.10.10.2 is this MAC address right here. So we'll go ahead and copy that MAC address and we're going to create an access list that filters that client from talking to that particular MAC address. So it's called a MAC access list. We're going to create that as extended because I want to filter based on the destination, not the source. If I was filtering based on the source, I could use a standard MAC access list. And we're just going to use a named approach. We're going to call it a MAC ACL. So I'm going to come into ASW1, config T, MAC access list. Extended is the only option in this case. We don't have a standard option. And then we apply the name. So MAC-filter. Okay? Now we still have permit, deny, and that's pretty much it. Just like any other access list, we have a permit or deny option. So I'm going to do a deny, the source MAC address. If I wanted to, I could specify my MAC address, which is this MAC. So PC1 is this MAC address, so I'll put that in there. All right. And then I can specify the mask for the MAC address. Now, this is where it gets a little bit interesting because we would use wildcard masking the same way in this case, but remember, we're dealing with hexadecimal values. We're dealing with hexadecimal values, which means that we have, for every hexadecimal character, we have, well, 4 bits, right? Each hexadecimal character is 4 bits. But you'll notice that it wants the mask written in hexadecimal format. So an F would mean I don't care. A 0 would mean all the bits matter. Does that make sense? A 1 would mean only the first bit we don't care about. A 2 would mean that the first 2 bits we don't care about, and so on. So you have to represent the binary string. For example, an A would be the first bit and the third bit we wouldn't care about, because A is 10, which is 1010. And I would have to match that to the corresponding 4 bits in the MAC address. Right? Now in our particular case, we're doing it on a specific host. So I could just put all zeros if I wanted to, but in this case it would probably be easier just to put the word host. That's going to allow us to identify that we're matching against a specific MAC address. All right? Now it wants me to specify the destination MAC address. And remember, I'm trying to block PC1 from talking to PC2. This is the MAC address of PC2. Again, I'll use the host keyword, and that's it. Right? Now you can see there's a whole bunch of other options that I have here. And it's kind of like getting into the options that we have with layer 2 frames. So most likely the option that we would match against could be ether type if we wanted to match against ether type. We don't care. We're matching against all types of layer 2 traffic. All right, but now I have to have a permit any for the remaining communication. So I'm blocking PC1 from talking to PC2, but I'm permitting all other traffic on that interface. Now I'm going to go into interface gig 00, and I'm going to apply that MAC access list by using the MAC access group command inbound to that interface. MAC access group, and what did I call it? MAC permit or MAC filter in. Okay, so let's go ahead and take that off real quick. I'm going to do a persistent ping here. Well, extended ping. Let's ping 10.10.10.2, repeat 10,000. So it's working just fine. I apply the access list. That should have stopped working. Why the heck did... Sorry? Oh, I had an L in front of it?
Yeah.
All right, let's go ahead and start that ping again. I did?
Yeah, press up arrow. If you go over ahead, it did have no in there.
No, because that would have given me an error.
Maybe not.
So the question is, why is the filter not working? Let's go ahead and do a little investigation. So let's do show run interface gig 00. We do have the MAC access group MAC filter applied. I'm curious though what the source of that ping would be. Let's make sure I got my MAC addresses correct. So B500 do show run, do show access list. Most likely I just messed up the MAC addresses. So 0C834F7 Bravo B500, that looks right. Nope. 0C834F7 Bravo, 4F7 Bravo B500. And the destination is 0 Charlie 834F Delta 1 F600. So that looks correct. You can see here that it seems to be matching the permit any. So that's actually an interesting concept. We are seeing that there are matches against the access list. But let me check my diagram here, make sure that I have the right interfaces. Gig 00, gig 00. So the access list should be working. I'm going to try one more thing. Let me do a debug IP ICMP. Let's try the ping again. And let's see what we're... So let's see what the ARP cache looks like on here. 4FD1 F600. Well, that's interesting. Everything appears to be correct. And we're definitely matching the access list, but it does not appear as though... I'm going to try one more thing. MAC access dash list extended. Try one more thing. It might be the way that this IOSV is working in GNS3. So I'm going to try this. Deny any host it's not letting me add a line. Do show access dash list. Oh, it doesn't have line numbers. All right, let's do this instead. Let's do no access no MAC access dash list. Extended. All right, we'll go ahead and put it back in. But what I want to do in this case is I'm going to do MAC access dash list extended MAC filter. And I'm going to do a deny just on the destination, as opposed to the source and the destination. I have a feeling that what's happening is, with the way this software works, that it's not recognizing that source MAC address. That's a possibility. All right, let's see, show MAC access dash, or show access list. So we're still getting matches against the permit any. Let me do this. Show interface GI00. That is the right MAC address. 0 Charlie 8347 4F 7 Bravo B500. Show interface GI00. 4 Foxtrot Delta 1 F600. That's very interesting. It should be denying that data flow. It's definitely the correct address. Well, that's interesting as well. Oh, let me do a show run interface GI00. MAC access group, MAC filter in.
You have to do it too.
That is the appropriate interface. Okay. Well, it doesn't appear to be working at layer 2, but let's go ahead and try it at layer 3, because we do have the capability of also applying an IP access list to the interface. I'm not sure. I think it has something to do with this viral image as to why it's not filtering, because it's a pretty basic concept, right? You're matching against the layer 2 frame information. If I was to do a Wireshark capture, I would see that that frame information is exactly what we would expect. In fact, let's do that. But we can also do a filter at layer 3 as well. And we'll go ahead and try and do that at layer 3. So let's see what happens here with this capture. Just to make sure that, you know, something's not being modified in the ping process by this software. So the source MAC is, yep, 0C834FD1F600. And the source MAC is 0C834F7 Bravo B500. So it's definitely, the MAC addresses are definitely correct within the layer 2 frame. It's very interesting that it's not doing what it's supposed to be doing. So, but we'll move on. We can also apply an IP access list, which is kind of interesting because we're applying a port-based ACL that's looking at layer 3 information, but filtering, it's a layer 2 interface, but it's filtering a layer 3 information. So this is just basically your standard access list or standard IP access list. So let's go into ASW1, config T, IP access dash list extended, and we'll just say IP filter. All right, we're going to say deny IP. We're going to deny all protocols. When you specify the protocol of IP, it includes every other protocol. But you can see there's a whole list of protocols that we have as a choice. I could deny OSPF. I could deny based on the protocol number. So like EIGRP would be protocol 88 and OSPF would be protocol 89 and so on. But if I specify IP, it includes all protocols. And we're going to go ahead and specify the source as 10, let's do a host 10.10.10.1 to host 10.10.10.2. All right. And we're going to do a permit any to permit the remaining, permit IP any, sorry, to permit the remaining communication so that that host can talk to other devices. Then I'll go into interface gig 00, IP access group, specify the name of the access list, and then apply that inbound. All right, now if this doesn't work, it's got to be something to do with the software not really recognizing that these ACLs are applied to the interface, but let's give it a shot. That actually worked, okay? So there must be something going on with the layer 2 filtering, because again, it's the same basic concept. We're filtering based on the frame information, not the packet header information.
Most of the time you don't use MAC addresses.
True. That is very true. We can still, as you can see, reach other destinations. So if I do a show IP interface gig 00, we can see from this output that we actually do have an access list applied. All right, right here. Well, see, that's interesting. Oh, that would be because that's the wrong device. Show IP interface gig 00. I was going to say that's interesting. It doesn't, it's not showing me that there's an access list applied, but we can see that here. Gig 00 is up, and we have an inbound access list applied to that interface. If I do a show access list, I can see in this case that we're actually matching 2 packets that were denied to 10.2 and the remaining packets matched to the rest of the network, or in this case 10.10.10.20. This is interesting though. So it appears as though we are matching the rules. This access list is no longer applied because you can't apply a layer 2 filter inbound and a layer 3 filter inbound. If I do a show run, interface gig 00, you'll notice that they're both there, but when I do a show IP interface gig 00, well, that actually makes sense. I wonder if I do a show interface gig 00 if it will show the MAC filter there. Because show IP interface would be all my layer 3 characteristics, and a MAC filter is not a layer 3 characteristic. So it's interesting that it doesn't show up in that regard, but it kind of makes sense, right? Because a MAC filter is a layer 2 filter, not a layer 3 filter. I'm a little disappointed that the MAC filter didn't work, but that's okay. We'll move on. All right. Another option that we have is to do a VLAN ACL. Now this is a really interesting concept. And by the way, something that we actually tend to use on a regular basis. If we know that they exist, then you'll have a good understanding of why you would perhaps want to use one of these filters, because of the amount of flexibility that it has in how we're blocking traffic within a VLAN. All right? We use something called VLAN maps in this case. And the other interesting thing is that VLAN filters don't imply a direction. We don't configure a direction for the filter itself. The direction is implied based on what you're trying to match against. Okay? So, in other words, the source and destination of the rule implies the direction of the traffic flow. So, we have a whole bunch of rules that we can apply, and then we simply apply the traffic to the VLAN. So let's say take a look at the example that they have here, and let's see if we can duplicate that example. Let me go back to ASW1, no access, no IP access dash list extended IP filter. I'm going to take out the old stuff here, and no MAC access list extended MAC filter. So we'll get rid of those. And let's do a show interface gig 00. So we're just going to take this show run interface gig 00. We'll just take out this config here. And we're going to now apply a VLAN filter as opposed to a interface specific IP filter or MAC filter. All right. We actually use these VLAN filters all the time. Not all the time, but often, because it does allow us to control what type of traffic is allowed within a VLAN. And if we want to deny certain types of traffic within the VLAN to all clients that are participating in that VLAN, we can use a VLAN filter to do that. So we're going to go ahead and create our access list like we normally would. Whatever we want to permit or deny, we're going to go ahead and configure. All right? So I'm trying to think of how we could apply this so that we could see how the direction is implied by the rule. So let's create an extended access list on ASW1. IP access list extended VLAN filter, and I'm going to do a permit ICMP host 10.10.10.1 to host 10.10.10.2 echo. So that means I'm allowing a ping, but I am not going to allow an echo reply. Because, and I'll show you why I'm doing this in a minute. Hopefully it'll work and that'll be great and we'll all rejoice. But I'll show you what I mean by not allowing the echo reply. Because a standard ACL, when we're working with regular access lists, we imply the direction by applying that access list to the interface in an inbound or outbound direction, right? With a VLAN filter, that's not the case. So now we're going to create a VLAN access map, and I'll just call it VLAN filter as well. So the syntax is VLAN access map, and then give it a name. VLAN access map, and we'll just call it VLAN filter. Doesn't matter if it's the same name. And then I'm going to match the access list that I just created. Match access IP address VLAN filter. So this is matching the access list that I created. And then I have an action that I can apply to that particular traffic. Do I want to allow that traffic or do I want to deny that traffic? Okay? So in this case, I'm going to say action forward. This is an interesting concept because we're using the access list to create a match condition for classification, but we're using the VLAN access map to actually apply the rule, the actual action that we're taking against the traffic. So whatever is permitted by the access list gets applied to this rule, if you will, which means I'm going to forward that traffic. I don't really need to specify anything else, because just like an access list, at the end of every VLAN access map, there's an implicit deny. So if it's not explicitly permitted, it will be implicitly denied. Then all I have to do is apply that filter to the VLAN. So I'm going to say VLAN filter and reference the VLAN filter. And then I'm going to reference the VLAN or VLANs that I want to apply this traffic to. VLAN list, in our case, VLAN 10. Now, if this did work, because PC1 is in VLAN 10, right, I should be able to send out pings, but I should not get a reply. So let's go ahead and try that. Ping 10.10.10.2. So the ping is not working, but we can always tell if the ping is allowed out because I can see that the PC2 is getting the ping. It's getting the echo request. It's sending the echo reply, but the echo reply is being denied by the VLAN filter. You see what I'm saying? The reason why this is so useful, I'll give you an example where we use these filters. A guest wireless network, where somebody is attaching to a guest wireless network in a particular VLAN, but we only want them to be able to get to the internet. We don't want them to be able to run any other protocol. So we would create a VLAN filter for that VLAN that would deny any communication outside of the VLAN to other specific subnets within the enterprise, and then allow everything else, as long as it was port 80 or port 443. So, and the nice thing about that is that anybody that's connecting to that VLAN, that rule would be applied. So we don't have to worry about which interfaces they're connecting to. As long as they're a member of that VLAN, that rule would apply. So just to do a show run section access map, just to confirm, we can go ahead and this is the rule that we have, which references I probably should have called them different names because then it's a little confusing, but the access list VLAN filter. So if I do a show run section access dash list, now let's go ahead and modify this rule to allow the echo reply, right? So I can come in here and IP access dash list extended VLAN dash filter, and I can say permit ICMP host 10.10.10.2 echo dash reply. Should give me the option. Oh, probably have to just put in host 10.10.10.1 echo dash reply. Okay, so now I'm allowing the ping to come back, and I should be able to ping that client now. But I should not be able to ping 10.10.10.254, which is my gateway. All right. Which, by the way, I've kind of blocked my client from even going out of the network altogether, because the only thing that I actually permitted was a ping, and a ping to an individual host. It's just an interesting concept, and it's just another way of applying traffic filters to different types of traffic. So another concern that we have with switches is MAC spoofing attacks. A MAC spoofing attack is simply where the attacker spoofs the MAC address of a victim. It can either be for the purposes of poisoning information to a particular destination, or maybe for the purposes of inserting myself into the middle of the conversation, like a man-in-the-middle attack. Now, there's a couple ways that we can protect against MAC spoofing attacks. The most common is to simply use port security, all right, which says that we're only going to allow a certain MAC address on a certain interface. Now, that doesn't prevent somebody from duplicating a MAC address. It might block that traffic on that port unless that MAC address, unless it's like a dynamic port security port where we don't really care what the MAC address is. We just want to make sure that the MAC address is, that we're only allowing one MAC address. Another way to mitigate the possibility of a MAC spoofing attack, it's a little bit more advanced, is to run something called dynamic ARP inspection with DHCP snooping. And we'll take a look at that a little bit later on. So we also talked about the idea of a CAM overflow attack. Can't remember if we talked about it in this class or the CCNA portion, but the switch itself has a finite amount of space for MAC addresses. If I come into my switch, let's go ahead and remove the VLAN filter, config T, no VLAN filter, what did I call it? VLAN filter. Going to make me put the whole thing in there. VLAN list 10. So we can make sure that we're not filtering any of our traffic. Let me try and ping my gateway again. All right, should be good there. All right, so if I go into a switch and I do a show MAC address table, if I look at the well, the MAC address table obviously is a list of all the MAC addresses that we've learned. But if I look at the aging time, we can see that the default global MAC address aging time is 300 seconds. So that means that if a MAC address is learned, regardless of whether or not we hear any information from that host, that MAC address will be written to that interface for 300 seconds. Unless we hear that MAC address on a different interface. Now, this is an interesting concept. What happens if I hear the same MAC address on two different interfaces? So let's say I've got 0 Charlie 8344 Foxtrot 7 Bravo 500 on gig 00. I'm going to go ahead and assign that MAC address to the interface on PC2. So let's do undebug all first of all. Config T, interface gig 00, MAC address. So I change the MAC address of the interface, do show interface gig 00, show interface gig 00. So we now have this MAC address on this interface on PC2. And if I do a show interface gig 00, so this would be an example of me spoofing a MAC address. I have B500 on this interface, and I have the B500 on this interface. Now what will happen is if I do a ping to my gateway, the ping goes through just fine. Show MAC address table. Try that again. I'll get there eventually. So B500 is on, well, that's interesting. It says gig 01. But PC1 is on gig 00. So it's showing this MAC address on gig 01. Notice I'm not even seeing an entry. That's kind of weird. I'm not even seeing an entry for gig 00. This one's still here because it hasn't aged out yet. That one will eventually age out. I'm curious why it's not. Let me just go ahead and do this. Let's pick a MAC address that is easy to dead beef for dad. All right. And we'll do the same thing on PC2. Interface gig 00, MAC address dead beef for dad. All right, so now we're seeing dead beef for dad on gig 00. So if I go to PC2 and I do a ping to 10.10.10.254, the ping goes through. And now we're seeing deadbeat for dad on gig 01. So once a MAC address has been learned, it can change if I see that MAC address on the other interface. Now what should happen, this is what I was curious about, is it should go back to gig 00 once I do the ping from here. And essentially that MAC address will start flapping between two different interfaces. If it does it quickly enough, you'll actually start to get warnings that says MAC address is flapping between two interfaces because it doesn't look like normal behavior. I'll bet you if I do a ping to that client that it will kind of freak out. Yeah, it's not going to work because the PC is, in order for this PC to generate the ping, it's going to have to do an ARP request, but it's not going to do an ARP request for a MAC address that it has. I already have that MAC address, so I'm not going to try and resolve that MAC address. If I do a show ARP, that MAC address is already in my cache. So I am, some weird things are happening. But if these clients, I know what I can do. I can ping 10.10.10.254 repeat and do the same thing on PC2. And I should, if the switch is doing what it's supposed to be doing, which it's not, but I should see potentially that MAC address is flapping. I'm not getting any indication of that, but I've seen that before where a MAC address will move very quickly. Maybe it's not doing it quickly enough, but it would move very quickly from one port to the other. And yeah, so our pings are definitely freaking out here. So it looks like this ping is working, then the ping is failing. This ping is working, then the ping is failing. So definitely a problem, right? If we're spoofing a MAC address, it's going to cause a problem in the network. Okay? So the other aspect that I wanted to talk about is this CAM overflow attack. Switches either forward or flood frames. The more the switch learns about the clients that are attached to the network, the more efficient the switch becomes, because what it ends up doing is just simply forwarding frames and it stops flooding frames. Okay? Now what does that mean? That means that if I've got PCB here and PCD here that are communicating with each other, initially that traffic might be flooded out of all the interfaces and the attacker might be able to see that traffic. But as the switch builds its MAC address table, that traffic now is going to only pass between those two interfaces. By nature, that's what a switch does. It forwards frames when it knows the destination MAC address, which means that the attacker is no longer going to see that traffic. Because the switch says, I know where MAC address D is, I know where MAC address B is, so I'm going to go ahead and just simply forward that traffic rather than flood it between those two interfaces. So the goal of the attacker in this particular case is to simply make it so MAC address B and MAC address D can't go into the database. This is not as easy as it may sound because you would have to flood the database with a bunch of bogus MAC addresses before B and D ever communicated, but that's what happens. The attacker starts to send in a whole bunch of bogus frames, spoofing a bunch of different MAC addresses to the point where it fills up the CAM table with all that bogus information, which means that B and D cannot be added to the MAC address table because there's no more space. And then the switch just simply starts flooding B and D's traffic, so now I can get a copy of that traffic. Practically speaking, this is probably not all that practical to do because you would actually literally have to flood that switch with enough MAC addresses to fill up the table before anybody else communicated and their MAC addresses were learned. And by the way, you'd have to continue flooding because the aging timer would time out for the MAC addresses you're sending in. And those MAC addresses would be removed from the database, and then all of a sudden legitimate MAC addresses could be added at that point. So it's an interesting concept, but I would say that it's probably not the most common type of attack that you would see. More commonly would be just a simple spoofing attack, where you're spoofing an individual MAC address for the purposes of intercepting that information for that particular client. In any event, what we use to protect against this is port security. All right? Port security is a way for us to identify what MAC addresses are allowed on what interfaces. And there's three ways that we can implement port security. We can implement it with a static configuration. We can implement it as a dynamic configuration, or we can implement it as a sticky configuration. Now, we did talk about port security in the CCNA, but we'll go ahead and talk about it again. There's a couple of caveats to implementing port security, and kind of really the easiest way to identify how port security works is to configure it. So we're going to go into our access layer switch, and we're going to set up a port security policy. And I'm just going to kind of talk about the different configuration options that we have, and we'll do some verifications and so on. So let's say that on port 1 of our topology here, or gig 00, I want to allow 3 MAC addresses. I don't care what MAC addresses they are, but I only want to allow 3. And by the way, if I get more than 3, I want to shut down the port. That's called dynamic port security. I don't care which clients are connecting. All I care about is how many clients are connecting. Okay? So I'm going to go into ASW1, interface gig 00. This is already done, but you would have to put in the switch port mode access command to start, because you cannot run port security on dynamic ports that are running DTP. So the port either has to be a trunk port or it has to be a static access port. Then I can set up the properties of my port security configuration. Switch port security maximum allows me to identify the maximum number of MAC addresses. Now you can see 4,097 MAC addresses this switch will support. I'm going to go ahead and specify that we're only going to allow 3 MAC addresses. Pretty straightforward. Switch port security violation. We have 3 different violation modes that are available with port security. Shutdown is the easiest one to understand. It also happens to be the default. If there is a violation on the port, we're going to shut down the port. Okay? And it does that based on error disable. What about protect and restrict? Protect and restrict essentially do the same thing. The only difference between protect and restrict is whether or not reporting takes place. Restrict will actually send out a syslog message. Restrict will send out an SNMP trap if you have SNMP configured. And restrict will increment the security violation counter. But protect will not do any of those things. The other thing about restrict and protect that makes them more useful is that they only block the offending host. They don't block any of the hosts that are not violating the policy. Whereas shutdown, if I type a violation mode of shutdown, if a violation occurs, the entire interface goes down, and it's going to affect anybody that's connected to that interface, including the clients that are actually following the rules. I know that the DoD loves to use the shutdown option because we always err on the side of caution when it comes to security. In the private sector, it's not so much. We tend to use probably restrict because we really only want to block the clients that are breaking the rules. We don't really want to block the clients that are not breaking the rules. All right? So I've got my switch port security maximum 3, says I'm going to allow 3 MAC addresses. I've got my violation mode set to shutdown. The only thing left is to simply turn on the feature. And that's switch port security. That command enables the port security feature on the interface. So if I do a show run, interface gig 00, I can see that we have our port security commands. Now the shutdown command is not listed there because that's the default. Usually in a Cisco device, the default stuff doesn't show up. If I do a show run all gig 00, it doesn't like that. Let me just do show run all. Show run all shows you everything that exists on this platform. And you can see that there is just a ton of stuff that's on by default that we never even consider or even know exists. But I mean, I'm not even past the first section yet. And look at all the stuff that's configured on this device, right? If you look at an actual interface, if I might actually be able to get there.
I think the only reason it didn't do it is because you didn't put interface.
All right. This is what's on the interface by default. It's crazy, right? These are all the commands that are actually applied to the interface by default. But if I do a show run interface gig 00, that's what shows up in my regular quote unquote running config. So there's a lot of stuff applied in these devices that we don't know about. But again, generally when we're applying something that's the default, it doesn't show up in the show run output. But I do have port security enabled. If I do a show port security interface, let's get out of show port security interface gig 00. I can see that port security is running on this interface. It is enabled on the interface. The port is presently up and it is secure. The violation mode is shut down. Aging time is absolute, meaning we're using the default aging time that's defined within the switch itself. We have a maximum of 3 MAC addresses allowed. It's already learned one of those MAC addresses. We can see that right here, deadbeef for dad, on VLAN 10. So if I come into my PC now, let me do let's go ahead and change the MAC first. Gig 00, MAC address, dead beef for who we want to give the beef to. It has to be somebody that has a hexadecimal name. Can't be mom, right? Let's just do A11, all right? Dead beef for all, okay? Now, if I go back and I do a show port security interface, well, let me generate some traffic. Do ping 10.10.10.254. All right. I should see that I've now learned 2 MAC addresses. Okay. Now, if I go and change my MAC address again, all right, I'm running out of creativity here, so I'm just going to put 3 C's. And if I do another ping, now I can see on gig 00 that I've learned 3 MAC addresses. And those will stay in there, by the way, for the aging time. The aging time is 300 seconds. If I do a show MAC address table, we can see that those MAC addresses have been allocated. Now what's interesting is they show up as static, even though they're not statically configured to the port. That's because they're tied to port security. Any MAC address that's tied to port security is going to be listed as a static MAC address in the MAC address table. So before our timer expires, let's go ahead and violate the port by changing the MAC address one more time.
You could have put Bob B0.
B0B? Yeah, we could do Bob. All right. So again, I'm generating the traffic, and now we see that a violation has occurred. Port security violation, error detected on gig 00, putting gig 00 in an error disabled state. The port is now down. Okay? Now the only way to recover this port is to fix the violation and then go into the interface and do a shut, no shut. Well, that's the only way to recover it manually. We could actually recover the port by using something called error disable recovery. So I can come into my switch here and I can say error disable recovery cause, P secure. I thought it was P secure. Let me see. Yeah, P secure violation. Oh, I just didn't type enough characters. P secure violation. So I'm saying I'm going to go ahead and recover the port based on a port security violation, and I'm going to recover that port. I think the lowest I can do is 30 seconds in 30 seconds. So I can program the switch to try to fix the port after a certain amount of time if I want to. Otherwise, it would require manual intervention. So within 30 seconds, I should see that that port attempts to recover itself. If there's still a violation occurring, the port will stay in error disabled state. There shouldn't be a violation still occurring because, well, there may be. It depends on how long in the aging cycle we are with the MAC address table. If I do a show MAC address table, nope, looks like we should be clear because those MAC addresses have cleared out of the MAC address table. So the port should automatically recover itself in about 5 seconds, I'm guessing. 3, 2, 1. That would have been cool if I actually got the time right. Right?
Exactly how good is he?
Yeah. But the port should recover itself. Let me do a show port security interface and see what the status is. So it's still shut down. I'm curious, it's been more than 30 seconds, why it hasn't recovered itself. Show run, include, error disable. Error disable recovery cause P secure violation. Error disable recovery interval 30 seconds. We also see here that there was a security violation that was counted. So it does keep track of the violations. I'm just very curious why the interface is not recovering. It should be.
Something like someone, just 300.
30 seconds is not that long. So that's curiouser and curiouser, as we say. Yeah, we do. I'm very curious why it's not recovering the port. Show run interface gig 00. Show interface gig 00. Port is still error disabled. I'm curious if iOS, I hate to blame it on the fact that we're using iOSV every time, but this is again a very basic concept. Error disable recovery allows the switch to automatically recover the port. Let's try it one more time. Let's go to interface gig 00 and go ahead and bring the port up. We'll do a shut and a no shut. And the port should come back up because we're not presently in a state of violation. Show interface gig 00. Now it's connected. And if I do a show port security interface gig 00, I should see that the port is secure and up. So the port's basically been reset. The violation count went back to 0. Generate some traffic. We should have now one MAC address that's learned. Well, that's interesting. I think there we go. Now I should have one MAC address that's learned. So let's go ahead and change the MAC address again. And we'll do it for Bob. There we go. Do our ping. So 2 MAC addresses. And again, let's do for dead beef is cool. All right. And we'll do one more ping. Now we're at our limit. And if I change the MAC address one more time. All right. Do my ping. Port security violation takes place. Port shut down. Now, let's see. Let me do a clear MAC address table. Well, see, won't let me do static. Do show MAC address table. Okay, so the port is down, the MAC addresses are gone, but the port, there it goes, attempting to recover the port. Okay, don't know why it didn't work the first time. Maybe because I enabled the error disable recovery after the port was already violated. So there may be an order of operations thing there, but it said, you know what? Oh, by the way, once the port goes down, any MAC addresses that would have been tied to that port go away anyway. The aging timer doesn't apply anymore because the port state went down. The switch is smart enough to say, well, there can't be any MAC addresses on a port that's not functioning, right? So that error disable recovery allowed me to recover the port automatically after 30 seconds. All right. Now, what are some of the other options? Let's say if I do a show run, interface gig 00, let's say that I only want to allow one MAC address on the port, and I want that MAC address to be written to the port once it's learned. All right, that's what we call sticky port security. So if I go into interface gig 00, I do switch port, port security, maximum 1. Let's change the violation mode as well. Switch port, port security, violation restrict, which should block only the offending host. And then I'm going to do a switch port, port security, MAC address sticky. All right. Let me see if it already stuck the MAC. Sometimes these devices are sending out traffic regardless. Show run, interface gig 00. I'm hoping it didn't. It already did. Okay. So you'll notice here that as soon as the MAC address was learned, it actually wrote the MAC address to the interface. I didn't put that command in. That's what sticky means. Sticky means as soon as you see the MAC address on the interface, go ahead and write that MAC address to the running config. So now that MAC address is permanently stuck to that interface. Not permanently, but it is stuck to that interface. So if I come in and I change the MAC address of the PC, right, and I try to do a ping, we get a violation. The port didn't shut down, right? I'm just getting a violation. And that's what restrict does. Restrict reports that a violation occurred, but it doesn't disable the port. So if I go back and I change my MAC address back, I don't remember which one I used, there we go. If I change my MAC address back, I should be able to ping because that MAC address was legitimate. That was the first MAC address that was written to the port, and that's the legitimate MAC address. So if I do a show port security interface gig 00, I can tell that there were 6 violations. Now, those violations mean 6 times a client tried to communicate on that port that wasn't supposed to. Because I was doing pings, right? Every time I generated a ping, it created a new violation. So restrict does report the violation. Let's change the mode to protect. Interface gig 00, switch port, port security, violation protect. All right. Now if I go to PC1 and I change my MAC address and I do my ping, the ping is going to fail and there won't be any indication on the switch that there was a violation. That is the only difference between protect and restrict. Protect does not generate any kind of notification. It doesn't increment the violation counter. It just passively sits back there and blocks the offending host. Does that make sense? Whereas restrict will actually generate those log messages and send and increase the violation counter, but it will still block the offending host. There's really not much else to port security. That's pretty much it. Protect, restrict, and shut down. How many MAC addresses am I going to allow on the interface? And what action do I take if there is a violation, right? Which is the protect, restrict, and shut down. All right, we did talk a little bit about the error disable recovery option as well. So that's what you see in the book here. Protect doesn't allow the traffic to flow for the offending host, I should say. It doesn't generate a syslog message. It doesn't increase the violation counter. Restrict does send a syslog message. Restrict does increase the violation counter. Neither of those shut down the port. And shutdown does send the messages and it shuts down the port. All right? So we go through a couple of examples here. This we did in our practical visual exercise there, so I think you guys saw all that. Show port security interface, a great way to verify whether or not port security is operational on the interface. There are some other commands you can run. You can do show port security address, for example, and that will give you a database, if you will, of the MAC addresses that are learned on the switch based on port security, how they were learned, in this case secure sticky, what interface, how much time is remaining before that particular entry gets removed from the port security database, and so on. All right? So this particular switch has the capability of learning 4,096 MAC addresses. That's based on the platform, the amount of memory that we have, and also the template that we're using for that we've used to allocate the memory that's going to store the MAC address information. All right. There's our show port security address command. All right. Now another topic that we're going to talk about, I'm almost positive that you guys probably are not familiar with. It's not very common. We have used it actually a couple of different times ourselves. It's called private VLANs. It's a very interesting concept. In order for me to actually do this though, I'm going to need to, let's go ahead and stop our capture right here. I am going to need to add an additional PC. So let me go ahead and do that. All right, so we'll have to configure this additional PC. The reason I wanted to add a third PC is because I want to be able to demonstrate this concept of isolated VLANs versus community VLANs. All right, private VLANs is a very interesting concept. It allows us to take a standard layer 2 broadcast domain and subdivide that layer 2 broadcast domain into secondary community or isolated domains. It's a really interesting concept. I'll give you some use cases of this a little bit later on, but let's go ahead and take a look at the basic configuration concept. Now, we know that we can protect traffic flowing from one VLAN to another by simply applying access rules or access control rules on our layer 3 interfaces between those VLANs. We could use an access list, or we could use various filters. We also saw that we had the ability to apply traffic restrictions using VLAN filters. The problem with the VLAN filter is it's kind of all or nothing, right? Or it can be pretty complicated because you have to define your rules very specifically as to what's going to be allowed and what's not allowed in the VLAN filter. But what if I said, in this case, I've got these 3 PCs, if you will, these 3 PCs right here are in VLAN 10. Now, normally, how would they be able to communicate? They'd be able to communicate with each other, no problem. We don't have any access lists filtering traffic. We don't have any VLAN filters filtering traffic. So those three PCs would be able to communicate to each other just fine. But what if I wanted to isolate this PC from talking to these two PCs within the VLAN? But I want these two PCs to talk to each other. There's a couple ways that you can do that. You can do a VLAN filter, and you can say 10.10.10.10 is not allowed to talk to anybody else in the 10.10.10.0 subnet, and that's, you know, pretty practical way of doing it. But we can also use what we call private VLANs. All right? If you look at the slide here, the primary VLAN is the VLAN that everybody's a member of. In our particular case, that's VLAN 10. Everybody's a member of VLAN 10. The secondary VLANs is how we subdivide that broadcast domain into separate logical broadcast domains within the VLAN itself. So again, all four of those clients are in a common subnet. So they're in the same broadcast domain, but we want to restrict the amount of data that can flow between those clients, or what types of data that can flow between those clients. So let's say in this case, this secondary VLAN, the yellow one here, is what we call a community VLAN. Anybody that gets placed into a community VLAN can talk to anybody else that's within that community. So host A and host B would be able to talk to each other, and they can talk to the router because we've identified the port that goes to the router as a promiscuous port. Okay? And let's say that the red secondary VLAN here is what we define as an isolated VLAN. That's a second type of secondary VLAN that you can have within private VLANs. So host C and D are in an isolated VLAN, which means that they are isolated from everybody else. They can't talk to each other. They can't talk to host A or B. The only interface that they can talk to is the promiscuous port. All right? And we're doing this, by the way, without having any access lists, without having to define any VLAN filters or port-based ACLs. We're just doing this simply by creating these primary and secondary VLANs. All right? And again, it's all happening within the broadcast domain. So the first step is to make sure that you define your primary VLAN, which in our case is going to be VLAN 10. Then you define your secondary VLANs. Never define the secondary VLANs first, because the secondary VLANs have to be associated to the primary VLAN. All right? And then you define your port roles. Is it a host port, which is then going to be associated to one of those secondary VLANs and then a primary VLAN? Or is it a promiscuous port, which is always associated to a primary VLAN, but then it's allowed to communicate to other secondary VLANs? We're actually not going to have a promiscuous port in our topology because we have a trunk. Promiscuous ports would be like a host port that goes to a router or something like that, or a firewall interface or whatever. So let's take a look at some of the restrictions. There's two types of secondary VLANs that we can create: isolated or community. All the clients that belong to the same community VLAN can talk to each other, but one community is not allowed to talk to another community. So they're kind of isolated from each other. And isolated ports can't talk to anybody except for promiscuous ports. You might be thinking, well, how would this be useful for me? How can I use this in a practical way? I'm going to show you how we've actually done this before. Okay? Here's an example. Let's say that this is not a router, but this is my firewall. And this is my DMZ. And we may have servers that sit on the DMZ, that the public internet has access to. But we have some concerns about whether or not there would be any vulnerabilities if a server in our DMZ was compromised. The DNS servers need to talk to each other, but the web server and the SMTP server, which are my proxies, are independent of the DNS servers and they're independent of each other. Now, if this was a normal DMZ environment, I could have a switch here that's in a common broadcast domain, a common subnet, and then I might have to put port-based ACLs or some sort of VLAN filter, what we call a VLAN ACL, on that switch to restrict traffic flow from the web servers to the DNS servers and vice versa. The problem is it can get kind of complicated because VLAN filters are, well, certainly port-based ACLs, you know, it's kind of like deny these protocols but allow everything else. Or in a VLAN filter, it's basically the same thing because you're using an access list as a match condition. It would be much simpler in our case if we could simply put the DNS servers into their own community and then put the web server and the SMTP server into an isolated VLAN. That's it. I don't have to create any access lists. I don't have to create any filters. It's an all or nothing concept. That's the only restriction here. It's an all or nothing concept. That is the benefit of a port-based ACL or a VLAN ACL over this particular option. Because at least with a port-based ACL or a VLAN ACL, you would have the choice to implement this or not. Excuse me, let me rephrase that. You'd have the choice to define what is restricted and what's not restricted by defining different rules in your access list. Does that make sense? Unfortunately, with private VLANs, you don't have the choice. It's all or nothing. Once a port becomes isolated, it can no longer communicate to other ports in that VLAN. So let's take a look at the configuration. We're, of course, going to apply this configuration to our topology. I just need to jump into PC0 and give it an IP address. So let me do that real quick. Host name PC0, interface gig 00, IP address 10.10.10.10, 255.255.255.0, no shut, IP route 0.0.0.0, 0.0.0.0.0, 10.10.10.254. All right. Ping 10.10.10.254. Make sure I have reachability. A couple pings might fail, but eventually I should. Oh, I forgot one more thing. The host port has to go into the VLAN. Need to do that. So config T interface gig 10, switch port mode access, switch port access VLAN 10. Oops. All right. All right. Now I should be able to do my ping, and everything should be great. You can do it. What is going on here? Make sure I got the right interface. Gig 10, gig 00. Okay. Show IP interface brief. 10.10.10.10. Show IP route. Although that would not be necessary. Try and ping 10.10.10.1. Well, that's strange. Let's do a show VLAN. Gig 10, show run interface gig 10. Show interface gig 10. It's connected. What did I do wrong? Do ping 10.10.10.254. Something is wrong. Can't get to my gateway anymore. Do I have a VLAN filter? I don't think so. I do. I thought I removed that. Well, I removed it from the VLAN list. Interesting. All right, let's just take that out. No VLAN access map. That's just the map. And let me do a quick show IP interface brief here. Show IP interface brief. So let's go ahead and try that again and see if we have connectivity. There we go. All right. That was the port security stuff that we had left over. So from PC0, I can now ping 10.10.10.1, and I can ping my gateway. So we've got connectivity. All right. And what we're going to do in our case is we're going to go ahead and make PC0 isolated, and we're going to make PC1 and PC2 part of a community. All right? The first step, and this is a critical aspect, is you cannot run, unless you're running VTP version 3, you cannot run private VLANs when you're in server mode or client mode. We'll talk more about VTP later on. So we're going to have to go ahead and change our VTP mode to transparent. That's going to be on our ASW switch. Remember, this is where we're configuring our private VLANs. If I do a show VTP status, I can see that my default VTP mode, the VLAN trunking protocol, is server mode. So I'm going to go VTP mode transparent, which will now allow me to create these private VLANs. The next step is to go ahead and create your secondary VLANs. So I'm going to go ahead and create VLAN 201 and VLAN 202. I want to do that first because then I'm going to associate those to my primary VLAN. So we're creating VLANs essentially the same way that we normally would, but in this case we're creating them as secondary VLANs. So I'm going to go in here and I'm going to say, let's do, in our case, I'll just document this, isolated is going to be VLAN 11, and the community is going to be VLAN 12. All right? So these two clients here are going to be in that community VLAN. Move this over here. Those two clients there are going to be in that community VLAN, and this PC over here is going to be in this isolated VLAN. So let's go ahead and create VLAN 11. And notice the syntax here. I want to use the private VLAN commands. I can still give the VLANs a name if I want to. We're not going to name them in this case. But I define the VLAN's function by using the private VLAN command. So I'm going to say private VLAN isolated for VLAN 11, VLAN 12, private VLAN community. There's no need to create more than one isolated VLAN, because isolated is just isolated. Once a client goes into isolated mode or into an isolated secondary VLAN, it can't talk to anybody else anyway. So there's really no need to create more than one isolated VLAN. You could have multiple community VLANs though, if you want to create multiple communities within the context of your private VLAN configuration. So I do VLAN 10, private VLAN primary. So I'm making VLAN 10 now part of this private VLAN configuration. But this is an absolutely critical step. I need to make sure that I associate the secondary VLANs that I created to that primary VLAN. All right? Because that's what ties everything together. So private VLAN association 10, oops, sorry, I was doing my regular VLANs, 11, 12. Remember, 11 and 12 is the isolated and community VLAN that we just created. So we've created our structure now. If I do a show VLAN, private VLAN, I can see that we have two secondary VLANs. VLAN 11 is isolated, and VLAN 12 is community. It's interesting that it shows the primary VLAN is not associated. Let me see if I had to get out of config mode. I've run into this before. Hopefully it'll work. I was hoping that with iOS V it would work. Show VLAN, private VLAN. Okay, it did take it. Good. If you're running GNS3 and you're using iOS or I'm trying to think of the name. We're using iOS V, which is kind of like what Cisco uses for viral. But you can also use, can't think of the stupid name of it now. There's another type of iOS that you can use that doesn't support the configuration of private VLANs. I was always curious if this version would support it, but looks like so far it's working, all right? So I've created all my secondary VLANs, I've created my primary VLAN. My next step is then to go ahead and map those VLANs to the ports. Now, if I had a layer 3 interface that was going to a firewall or going to an upstream router or something like that, I would want to go ahead and set up my promiscuous port. We're not going to do that in this case because trunk ports automatically pass traffic for all VLANs, including the secondary VLANs that you create. So a trunk port is just like a regular trunk port. And in our topology, that's what we have. We have a trunk port that goes up to DSW1. If this was a routed port, I would have to make this my promiscuous port. But because it's a trunk port, it's just going to act like a regular trunk. If I come into ASW1 and I do a show interface trunk, we can see that it looks just like a regular trunk. And as long as our primary VLAN is associated to that trunk, that's all that matters. Okay? So our goal is kind of just to isolate the traffic that's passing between these clients within the switch itself. So the last step is then to just go ahead and associate our host ports to their VLAN. So we're going to go into interface gig 10 in this case. Interface gig 10. And I'm going to use the command switch port mode. So instead of saying switch port mode access or switch port mode trunk, I'm going to say private VLAN host. Switch port mode, private VLAN host port. It's a host port. Now I also want to associate that port to its primary VLAN, that's the 10 in our case, and to the secondary VLAN, which in our case is going to be the 11 because that's what we set up as our isolated VLAN. So switch port private VLAN host association. Host association 10, 11. We're putting it into the primary VLAN of 10, and then we're associating that interface to the secondary VLAN of 11. If I go to interface range GI00-1, I can pretty much do all the same commands, host, but this time we're going to do a 12 because we put both of those interfaces into the community. Now, if everything worked, show VLAN, private VLAN, I should see the ports associated to their respective VLANs. Gig 00 and Gig 01 are in a community VLAN 12. Gig 10 is in the isolated VLAN 11. They should still be able to ping their gateway. They should. Oh, you know what? I think on ASW1, show run interface gig 33. Nope. Oh yeah. See, I have VLAN allowed. You need to allow your secondary VLANs across the trunk as well, not just your primary VLAN. So interface gig 33, switch port trunk allowed VLAN 10 through 12, comma 20.
Is this,
Oops, 10.
add command?
You can use the add command as well to add individual VLANs. So what he's saying is if I just wanted to add, I could just use the add command and I can add the VLANs. Make sure you don't just put in 11, right? Because that actually replaces the previous command that you had before, and now only 11 is allowed. All right, so I'm just going to do 10 through 12 and 20. Do show interface trunk. And now we can see all those VLANs are allowed. I'm still a little bit hesitant as to whether or not this is going to work, because let me go on DSW side as well and do the same thing. We don't have private VLANs configured on DSW. We might have to set up our private VLANs on DSW1 as well. I think we're going to have to do that. Switch port mode, let's do VTP mode transparent. All right, and let's do our VLAN 10, or sorry, VLAN 11, private VLAN isolated, and VLAN 12, private VLAN community, VLAN 10, private VLAN primary, and then we want to associate that VLAN. So we want to make sure that we associate that VLAN. So private VLAN association 11, 12. Interface gig 3.3. Switch port trunk allowed VLAN add 11 and 12. Do show run interface gig 3.3. Just make sure it, yep, okay. And in this case, our routed interfaces are our VLAN interfaces, okay? But I'm not sure that we need to set those up as promiscuous ports, because they're layer 3 interfaces. They're not a layer 2 interface that goes to a layer 3 interface. They're literally layer 3 interfaces. So if I went into interface VLAN 10, I would not be able to do a switch port command because it's not a switch port interface. So this is the only exception. We're not using a physical interface. But let me do a show private VLAN, or show VLAN private VLAN, to make sure that we've got the ports identified. Show interface trunk. So we're allowing all those VLANs. Let's go ahead and test this again. So this is where it gets a little bit strange with SVIs. I'm not sure how the SVI needs to be associated with the private VLAN configuration. If it was a routed port, I would simply make that port promiscuous. But I'm very curious as to why I would not be able to ping DSW1's VLAN interface. But anyway, we should still be able to ping from PC1 to PC2, because they're within a community on that same switch. So let's try and ping PC2 from PC1, ping 10.10.10.2. But if I try to ping 10.10.10.10, it should fail. And that's because 10.10.10.10 is in an isolated VLAN, and PC1 and PC2 are in a community with each other. So I'm very curious. Let's go ahead and do a capture here. And let's see if we can see the pings going across the trunk to the VLAN interface. Because if I ping 10.10.10.254, it should fail on PC1 as well. But I want to see if those pings are coming across. So the pings are coming across. Let's see what they look like. Open. There we go. So it is being tagged into the VLAN. We see it's a .1Q frame. It's being tagged into 12, which makes sense because that's the community VLAN that the client belongs to. But it's not able to go to the VLAN interface, which makes sense because there should be a promiscuous port that allows us to communicate to that interface. This is the first time I've ever done it to a VLAN interface as opposed to a physical switched interface to a router. Let's see if PC0 is coming in with VLAN 11. Ping 10.10.10.254. It should be coming in as 11. Oops, wrong packet. And yeah, it is getting tagged into VLAN 11. So that makes sense because those are the secondary VLANs that these clients belong to. So that part is working. And DSW1 is configured for private VLAN, so it understands what those tags are. But I'm very curious about how we can set this up to a SVI. So we had to map the, on the SVIs, we had to map the secondary VLANs to the SVI so that it understood that it was allowed to communicate to those secondary VLANs. It's kind of like taking a host port and mapping making that host port promiscuous. But because the SVI is a layer 3 interface, we can't really assign a VLAN to it, but there is a mapping that has to be done. Okay? And we mapped to VLANs 11 and 12, which were my secondary mappings. I thought it was wanting me to assign the primary VLAN to it, but it says, you know what, you can't map VLAN 10 to VLAN 10. So okay, yeah, that means that we're trying to map our secondary VLANs to the SVI. And our pings work just fine. I can ping the gateway, but I cannot ping 10.10.10.2, and I cannot ping 10.10.10.1. And that's because we isolated this PC to VLAN 11. These guys are part of VLAN 12. They're in a community VLAN, so they can ping each other, but they cannot ping DSW1. Kind of interesting. Actually, very interesting. All right. There is one more option, and I don't know if it's in the book. It is. I'm going to talk about this option. It's called the private VLAN edge configuration option. We use this a lot as well. In fact, this is even easier to use because I don't need secondary VLANs. I don't need primary VLANs. In fact, let me go ahead and clean up my configuration a little bit. I'm going to do a no VLAN 10 and 11, or no VLAN 11, no VLAN 12. Do show run interface gig 1/0. And I'm going to remove the private VLAN configuration. I'm only going to do this on a couple of ports because the concept is relatively simple. All right, we're going to do switch port mode access on that interface. So as far as gig 1.0 is concerned, it's just a regular access port now. And it's tied to the primary VLAN. Let me do a show VLAN real quick. I don't think we need to change VLAN 10's nature. It's still a primary VLAN. So let me do the same thing for our PC1. Do show run interface gig 00. And we're going to go into interface gig 00, do a switch port mode access, which really is all we should need to essentially get rid of its configuration with private VLANs, but we'll go ahead and take out that, and we'll take out the port security, even though it's not enabled. I just want to make sure it's a nice clean configuration. Do show run interface gig 00. So we've got essentially two clients, regular VLAN. They should be able to ping each other. PC0 should be able to ping PC1, no problem. All right? And it's not. All right, let me go back to ASW1. There's probably one more thing I need to do. VLAN 10. Let's do no VLAN 10. Let's just clean it all up because we had VLAN 10 set up as a private VLAN. No VLAN, VLAN 10. So now it should just be a regular VLAN. Show VLAN, private VLAN. We should not see VLAN 10 listed. Still listed there. Config T, VLAN 10, No private VLAN primary. Do show VLAN, private VLAN. No VLAN 11, no VLAN 12. Why isn't it taking it out? It says non-operational, so we'll give it a shot. All right, so the ping's going through, right? We got a regular VLAN, but I don't want PC0 to ever be able to talk to PC1. Ever. We already know that we could put them in isolated VLANs. They wouldn't be able to talk to each other, but you saw the configuration was kind of convoluted. There's a lot of different steps that we have to go through to create that. I could put in an access list. I know that. I could put in a port-based ACL. I could even put in a VLAN filter. But there's another way to do it. Config T, interface gig 10, switch port protected. Interface gig 00, switch port protected. Now PC0 will not be able to talk to PC1. Right? Well, it's easier, but there's a big difference. Protected ports can't talk to any other protected ports. So there's no distinction between IP address. There's no distinction of community versus isolated. It's just you either can talk or you can't talk. Protected ports cannot talk to other protected ports, period. Okay? Perfect example of this use case here. We had a customer that was a bank, and they had a firewall with a DMZ, and on that DMZ they had a switch that had a bunch of connections that went to other banks because they had to do a lot of transactional, they had to process a lot of private data, and they wanted VPNs and not VPNs, well, yeah, VPNs, but essentially point-to-point connections. Those banks on that DMZ switch should never be able to talk to each other. They should be able to talk to the firewall, but not talk to each other. So we just made all the ports protected on that switch, except for the uplink port to the firewall, which means that no traffic was allowed to pass between those ports on that switch. It didn't require the use of a VLAN filter. It didn't require the use of setting up. We could have done it with private VLANs, and we could have done it with an isolated private VLAN, but switch port protected is awesome because it just simply says any port that is protected, and it's local to the switch, any port that is protected cannot talk to another port that's protected. So it's a really, really simple scenario. We use this also in our hacking classes. When we have like a CEH or a GSEC class, we will actually have servers up in front, and it's all wired. And we'll make all of the PCs that go to the students protected, and the servers are unprotected, because you get into a hacking class and the students like to hack each other too. So we try to prevent that from happening. All right? All right, we made it through that chapter. Hopefully you learned some things in that chapter. It was a long one. So we'll see you guys in the next one.